So following the introduction, I would like to welcome Haralambos Tsurakakis. You want to move the window?
Yeah. Let me. It's in the recording.
Yeah, it doesn't matter. Yeah, we will. So welcome, Haralambos.
Okay, so hello everyone. It's my great pleasure to be here. So let's see if this works. Okay, excellent. Okay, so I'd like to begin by thanking Dimitris and Panos who organize this summer school. If you want, you can download the slides. They're available on Git. You can see the link here. So it's under my personal Git, Cyprus-EDBT25, in case you want to download the slides and keep track or take a peek in what follows. The goal, I would say, for today is to focus on graph analytics, with the main focus on being algorithmic techniques. The reason is these form the foundation for understanding graphs better. And I'll be using several established research results to illustrate very important fundamental concepts. So, for example, how many of you have heard of arboricity in a graph? Okay, we'll learn about this today. It's a very math-oriented definition, but it turns out that when you look into unsupervised node embeddings, the number of dimensions you need to have to encode the graph is order arboricity squared. So you can see how pure math concepts translate over to modern machine learning concepts as well. Let me put OK here. Okay, so one thing I'd like to note is I don't want to rush. There is a lot of material. I would like to receive more questions if, for example, something is not clear, or even if the intuition of something doesn't make sense, just stop me and we can discuss it and clarify, okay? Sounds good? Thank you. Okay, so we start with graphs. Maybe I'll go through this part a bit faster because you already saw this stuff yesterday with Ioanna. So we have a set of entities which form the set of vertices, and graphs model the pairwise relations between those entities. So we can have directions, we can have weights, and part of the reason why graphs are so popular is because they can model many real-world datasets. In one way to think about those datasets is some datasets are graphs to begin with, so they're very naturally given to you as a graph, but it's also frequently the case where the dataset has nothing to do with a graph, but you create some type of graph that encodes similarity or some other kind of structure that you're interested in. So, for example, a social network is naturally a graph. Okay, people who are friends are connected through edges. Computer networks are also naturally graphs. The internet, where the nodes are autonomous systems is basically, you can think of it informally as a collection of IPs and routers. Also are naturally modeled as graphs. Web pages, the web graph where nodes are web pages and you have hyperlinks, are also naturally modeled as graphs. Google became the top company by basically exploiting the graph structure compared to prior search companies that were based on content. So you used to go to Alta Vista and say, find me this web page related to Cyprus holidays. And they would look the keywords into a big set of web pages. Google, what it did, the famous PageRank algorithm, is basically think of the importance of nodes through the graph structure. So you are important if you are connected to many other important pages. And this gives a sort of recursive definition of importance, which ends up being mathematically encoded as a linear system. Okay, so the Google PageRank is nothing but a solution to a linear system. Proteins that interact. This actually, I've had this slide for a long time, but in today's world, you all know AlphaFold, right? So AlphaFold that gave the Nobel Prize to Demis Hassabis, who is partially from here, and Jumper from Google used protein interaction graphs, some residue protein interaction graphs. When did graph theory start? It started, if I recall correctly, in 1736, or definitely in the 18th century, when Leonhard Euler faced a riddle. So the residents of the city of Königsberg, they had, you can see the map of the city here, you can see there were bridges. And the question was whether they could start, let's say, from a given point and cross all bridges exactly once and end up to the very same point that they started from. So what Euler did, it mapped the problem to a graph problem. So he thought of the land masses as nodes and the bridges as edges. So he created a graph, and then he proved his famous theorem about what is known today as Eulerian graphs. The answer to this riddle was no. And the answer is you need to have every node having an even number of neighbors if you want to have this property. You can see that these nodes, they have 3 neighbors, and this destroys the property of Eulerian graphs. Any questions so far? Okay, so let's see a few graph data sets. Dimitri,
It's fine. It's just the online audience. They cannot see what you have a background. Can you remove the background from Zoom?
sure.
I'll do it for you. Hold on. Video. Then it's choose. Just.
Okay.
No. Okay, that's it.
Sounds good. I forgot to hit the button.
Yeah.
Sounds good. Okay. So yeah, graph datasets have a long history. We said that in the early days of graphs, they used to be small. You could inspect them and you could reveal a lot of information about them. So let me.
Okay.
Perfect. Okay. But nowadays we have more and larger networks, and these are products of technological advancement, ranging from pure technology to biology to brain scans and so on. So we have to deal with graphs that have, I would say, close up to trillions of edges nowadays. But billions is a common workload. Billions of edges is a common workload. And you've seen discussions before. It was about reinforcement learning, but we also have deep graph models which have enabled breakthroughs in drug discovery, fraud detection, and many other applied areas. So it's a very exciting time. This is the internet map. You can see a nice visualization. As I said, the nodes are autonomous systems, and basically the edges are created by looking at trace route data. Using the PGP protocol. So you can see, for example, some very high degree nodes with, let's say, this yellow over there. These are, let's say, tier 1 nodes, and then you can see this star-like structure. So it's a nice picture, but to analyze these large graphs, we need more algorithmic tools besides visualization. Not to mention that even those visualizations are created using sophisticated graph algorithms. So many types of networks: social networks, knowledge graphs, technology networks, biological networks, supply chain networks are very important as well. Blockchain, you all heard about crypto and so on. And in general, financial networks where one person sends an amount, could be money, could be number of tokens, to another wallet or person. Protein contact graphs, residue interaction networks used by AlphaFold, and many others. So I don't want to take too much time because we have a lot of algorithmic material, and I know that Ioana went through some of this stuff I found out today. But basically, you can see that social networks, we have links that denote a social interaction. This could be phone call networks. Who did you call? Okay, it could be undirected in the sense that 2 entities had a call, or you would perhaps like to encode who called whom. So it could be directed as well. Email networks, who sends an email to whom, instant messaging networks, sexual networks that are have been studied by MDs, by doctors, to understand the propagation of diseases like sexually transmitted diseases. and of course, collaboration networks such as co-authorship or co-acting or co-directing networks. Knowledge and information networks, we typically refer to such graphs when they have nodes that store information. For example, the web, classic information network, the nodes correspond to web pages that they store text, okay? And the edges correspond to hyperlinks. Peer-to-peer networks, if you see this list, they actually have this type of property where the nodes are associated with some type of attributes or some type of information. Technological networks, such as power grids, telephone networks, they play a very crucial role in our today's life. For example, if your Facebook stops working today, you may get frustrated, but if such a network breaks down, people have frozen. Let me give you an example. This is the US power grid. Just by visualizing this, you can actually see the more densely populated areas compared to these areas. But one of the key reasons why people study these networks is because they want to understand the cascade of failures. For example, in 2003, few trees in Ohio, they fell and destroyed a few cables, and then this failure cascaded up to Toronto, up to Canada, and several other states around this area. So by looking at this network, one would like to understand the resilience, the probability of failure of edges, and also in a probabilistic way, if a failure happens there, what's the probability that this part will get affected? So there's a lot of probability also involved in the analysis of networks. Biological networks, I've mentioned them several times. We have people who study zoologists, the species or who eats whom type of networks. The fox eats a rat or rabbit, and so on. This gives a much better understanding of how various types of animals interact with each other. Metabolic pathways, cancer pathways. People try to understand, create networks essentially from cancer patient data that capture the progression of a disease. For example, in breast tumor cancer, if you have a P53 mutation, then it can be the initiator for more mutations. So this can be encoded as oncogenetic trees or more complex oncogenetic DAGs, for example. By DAG, I mean directed acyclic graph. And as I said, if I say something out of habit, like an acronym that you don't know, just stop me and I'll explain. And then we have data sets that, as I said, are not naturally, they're not given to you as a network, but for example, you may have this like social media type photo sharing site like Instagram or Flickr from the past, where basically users upload photos and then you can see that they geotag them, they connect to other people, people press likes or comment, and this type of platforms, they create a very rich framework for graphs. For example, when I spent some time in Facebook research, we're looking into node embeddings from graphs created from Instagram type interactions to embed the nodes in some space and then use these vectors, as Dimitris was talking earlier about vector databases, to make better recommendations. So, for example, you can have nodes being photos, tags, users, groups, various types of entities. You can have edges of different types. This naturally creates what we call today as nodes. Exactly. One sec. The mute button. Okay. That should work. So then we can create many different types of graphs. Here, for example, we can have tag graphs or tag users, or user graphs based on favorites, based on discussions, and so on. And in industry, of course, choosing such a graph is not an easy choice, and you may want to encode all the information as a knowledge graph and query that knowledge graph. So recurring theme, we have different user interactions in this example, and this can be of posting, comment, like, marking, and so on. And all these interactions can be naturally modeled as graphs. Okay. But you can also create image similarity networks, where nodes are images and you have some measure of similarity between photos, and you create a network where you may give a query and find images that are similar to this query node. At least in the early days, this Google search image, it was doing something like that in the early days of the tool. So another theme which is more modern is node embeddings, which is basically mapping nodes to some space. We'll talk time permitted for Euclidean spaces. And these embeddings are optimizing some objective depending on what structure you may want to encode. And they're being used very widely on tasks like classification, recommendation, and link prediction. And there were a breakthrough, especially the first paper of DeepHawk, in the sense that these tasks had been there, and we had benchmarks, and we had performance, and then suddenly these embeddings came, and the performance improved by a lot. Then we had Node2Vec and other unsupervised node embeddings. So Pinterest, where Yura Leskovets was actually an advisor participating in the company, they were using Node2Vec to recommend pins based on user-item interaction graphs. So you have users, you have items, and then you want to make recommendations. This is very similar to what I was mentioning earlier about my experience with Facebook and doing recommendations on Instagram to users of products, where the product in Instagram are some other users in reality, are some certain accounts. And Alibaba applied DeepHawk style embeddings to model behavior graphs in fraud detection. So lots of motivation here. AlphaFold, as I mentioned earlier, their method is not strictly speaking a standard off-the-shelf graph neural network, but it has many ideas coming from graph neural nets. So you see again how graphs, together with labels and certain modern tools like attention, receptive fields, and so on, can basically make huge breakthroughs. Okay, this paper, they received the Nobel Prize. The potential of curing diseases from this thing are significant. Talking to people from Boston who work in bioengineering and the medical field, they see huge potential in the future from AI and graphs in drug discovery and many other important aspects. So graph neural nets, which I just mentioned, as I said, they're tools that combine graphs, neural networks. They're used in drug discovery, in knowledge graph completion, in understanding traffic on roads. So this can lead to optimizations by making the best interventions. Code intelligence, actually, if you think about source code, it forms syntax trees, right? And these are dependency graphs. So lots of automation in terms of coding, even generating automatically test instances. Graph neural nets are being used in this context. Cybersecurity, especially for anomalous behavior, and zero-day attack detection. They have many success cases. In financial tech, in social networks, they're all over. So currently I'm involved in a startup company, which is called Relational AI. And this startup is bringing together graph reasoning together with rule-based workflows. And it offers both predictive and prescriptive logic directly into the observability stack on the cloud in Snowflake. I'll show you a little bit, some demo of a notebook, and it's not something you can generate though, because it's like privately owned and you need to have an account to do that on Snowflake. But just to give an idea how this stack workflow looks like. And it's founded, one thing I would like to point out is that this company is founded, the intellectual property is essentially theory. So basically, how do you do joins in graph database systems in an optimal way? In the sense of optimality that we have taken is the worst case optimal joins. That means that you are guaranteed that your runtime is essentially linear to the worst case possible output size that you can have from a query, which is a lower bound, right? If a query is that large, you need to spend this amount of time. Okay, So one thing about relational AI, despite being a product that
Can you say one word additional to that? I mean,
Yeah.
we know in databases they are not using it. Let's say, system are used lefty plots, for instance, just to minimize the number of computations of the evaluation plans.
Yeah.
And I mean, how do you go about computing the optimality? This is like
There are-
a known theory for.
I'll go together to I'll touch this topic in the context of the simplest query, but in general, I can give pointers to those interested. But based on tools from information theory, you can actually create plans that follow step by step the mathematical proof of how you break down the joints. For example, I'll give you an example. If you have, let's say, I can give you a relation where basically it's like 3 joints, and if you do any of the 2 binary joints, no matter what, the intermediate output size can explode. So this is the issue in general, that why is this a difficult task, okay? The task is you have joints which can be complicated, and the intermediate steps can be significantly larger than the final output. So this is where this idea comes from, and I'll say a few words in the context of the triangle query. So so these are like 7 deadly sins, which I actually have heard from Bob Mulia, who is one of the important figures in terms of businessmen and founders of the company. And he was also involved in Snowflake, another multi-billion-dollar company. These are 7 sins which I think are very nice to keep in mind when you build a data management system. You don't want to have a data breach. You don't want to have unauthorized access to sensitive data. You have data loss or corruption. This is very bad if you lose your data or it gets spoiled. If the data management system returns wrong results, that's not good. It's bad news. Service disruption. It's very common. Unfortunately, and there's a lot of effort in industry to make sure that the service is not getting disrupted. Billing errors, unannounced behavior changes, and query failures. So these are 7 things that you need to avoid if you want to be reliable to your customer, okay? And relational AI, so far, has built a very trustworthy data system which defends against all these 7 sins. So I would like to, perhaps before I start the background, because I want to make this self-contained, there are some involved concepts and I want to go through some background, which is part of Let's Think About It course. Feel free to tell me this is fast, we know it, and I can go faster. But what I'd like to show you for a second is the website of the company. Let's see. So let's see. This is, let's say, the documentation for this system. Let me just search something simple. Number of nodes. So let's click on one. I just want to show you a demo how you create this stuff. So you can see here, let me show with a pointer, that basically you make some imports in Python. So you write in Python, you create a model. What is a model? Essentially, it's a database. So by specifying this model, you create a database that has this given name. And then you can create different entities, person, friendship, whatever you actually want to encode. And you can add, let's say, entities, Alice and Bob to the person. And you can also make multi-valued relations. So for example, you can say, I want to have a property of Alice, let's call it friends, where I add Bob. So this is like encoding a very simple graph. And Bob adds Alice. Then you take the model. So basically, you can think the model as a database, okay? It's on the cloud. It's on Snowflake. This demo is like, you can do it locally, but in general, your data may lie on the cloud, and you may want to read it, as I can show you on another notebook. But basically, you create a graph. This is a node set, this is the edge set, and then you just make a query and you say, I want to compute the number of nodes. And as in SQL, you may get a select, and you may output that the number of nodes here is 2, Bob and Alice. This is a very small demo, and what I want to show, maybe right here. So in reality, it's a bit more complicated. For example, you can see here that
it will stabilize. Give it this.
Okay, so what I want to show is that you basically do some imports, you create a model, and in reality, creating the graph from the data that lives on Snowflake is, this is a supply chain example. It's encoded as this function which lies in another file. You get the graph, and then you can query the graph. So basically, you can actually say, this is a simple example. Let me go further down. So, for example, I may want to compute the out degree or the reachability. These are concepts that we will discuss. But basically, you can see this is a performance experiment I was doing. It was all meant to be for the tutorial, but during lunch with Dimitris, we said it's a good idea to show you. So basically, you can see that I get an entity. This is the way this language is functioning. So basically, I'm getting an entity, and I want to compute the out degree of that specific entity. So this creates a full table where basically you have all the nodes and the out degree as a second column associated. And you can see that on the Visual Studio environment, I can see the transactions which take place between my local client and the cloud. I can actually go and look the logs and see what happened. I can see the query optimizer plan and everything. You can see here I have the engines, and you can see right here, it's my database. So here I have, let's say, my models. Currently, I need to run it again, but basically, you will see, you can see all the relations, all the functions essentially that the system provides, plus the ones that you can potentially incorporate, like I have done, for example, here, and I can patch this code on the model. So this is, for example, some, let's say, reachability functions that I was trying to benchmark these days. And you can actually see how it works. You can say reachable from, forget the naming, but basically you have a graph G, you have a node U, and a node V. V essentially is going to be the output. So what you're doing here is you're saying that basically the output is going to be part of the reachable from if it's if U is a node, so you want to make sure you ground the variable, so U is actually a node, and either U is equal to V, so basically U is reachable from itself, or there exists a W, some other node, such that you can go from U to W, and then there is an edge from W to V. So this is like a language. You can see how nicely you can write down the recursion, and then you rely on the smart query optimizer team, which takes this Datalog-like program. It's not Datalog, but it's inspired by Datalog. It's a language that they've developed in the company and produces an efficient execution plan. And this is where I said that there's a lot of algorithmic ideas playing a role. So, yep.
So is this closer to Datalog or
It's closer
to calculus?
Yeah, so it's basically inspired by Datalog, yeah, but it's not Datalog per se. There are differences, but in terms of model, it's the closest. So you have two prominent paradigms in SQL in querying. You have SQL-like languages, which has been dominating, and then Datalog, which is very nice and elegant theoretically. And I say theoretical because in SQL, if you want to write down recursions, if you try, you will understand what I mean. Okay, now you have ChatGPT, it can try, but in general, SQL is not meant to do recursion fast. Plus, it uses classical binary jobs traditionally, so it doesn't have this worst case optimality property. So here we have a combination of algorithmic ideas with elegant database theory in this language. So going back to the presentation.
In the back?
Yeah, please.
Is the data model the same as like a relational data model? So is it still like the data stored in normal Snowflake tables, or is it like a more graph structure that's
it is a very, very good idea. So basically the company has taken the trajectory where everything is a Snowflake table. and they have created a very efficient interface to be a co-processor of Snowflake. So everything, in theory, you can even query them with SQL, okay? But what this language provides you is, as I said, recursion, very efficient way of querying knowledge graphs. And it's a more general data management system. So you can have some knowledge graph plus some information about tax data. So you may want to create programs that say, I want something from the graph that combines some information from taxes, okay? So an example that I did recently for a customer was basically trying to find an anomaly. How many of you know Benford's law? Benford's law? Nobody? Okay, maybe I can open a link. Digression, but Benford's law, if you open a book, if you look the tax data, the distribution of the first digit is not uniform among the digits. So the digit number 1 appears more often than 2, more often than 3, and so on. So I think it's good to know. This is being used for trying to detect tax evasion. So Benford's law. So this is the probability that the first digit of numbers you see in natural data is number 1. So you can see, of course, 0 never appears as the first digit. Number 1 appears way more often than 9 as the first digit. So people have tried to detect fake election results and so on and so forth using this law, okay? So you may want to say, here's my data. I want to find, let's say, a path or a subgraph where Benford's law is being violated, okay? So you can do things like that.
Yeah. The way you explained it with relational Snowflake part is clear, and then you also have this very nice language for expressing graph basic logic.
Yeah.
Where is the AI part? Is this in
There is
the
AI. There is GNN engines and various other components that get integrated into the system. So
for the graph part or the
for the graph part, yeah. So it's let's say a big initiative to create, and actually the company won in some GNN competition. In one the top award, in another one the second award. So it's work under construction, but it's very.
So you have machine learning models somewhere as operators in this, or it's not part of the.
So in the GNN aspect, we're trying to incorporate ideas like when you have matrix multiplication, you can encode it as joins. You can encode many things as joins. So there has been an attempt to model machine learning using joins, but to the best of my knowledge, this team is using a hybrid of approaches. So they use existing toolboxes like PyTorch, but they also bring in ideas from relational data management to bring things together. So one very important thing is, like, you may see matrix multiplication and you may look like shortest path. So you can encode them as matrix multiplication in some way where the operators of plus and multiplication change. You may have different, basically semi-rings. But anyway, let's take it step by step. Did this answer your question, or?
Yes, I was just maybe one extension. Isn't then every edge traversal one join if you use like the relational model? Like if you have a node and you want to like reach another node, you would need to join, right? So
yeah,
like a traversal of 5 nodes would be 5 joins, right?
No, yeah, but you won't do it in this way. So join here, I mean, you have two. So that's a great question. And for example, in a 3-way join, let's say that I'm going to discuss, you may have to do multiple joins, but some cases you may not want to do them in. You may be able to reduce their number, or when you have to do a certain number, you can do them in an optimized way. Even the order according to which you join the variables can play a difference. Of course, it's a very hard problem, but in any case, yeah, very good question. Yes, George.
Can you say the key differences from Neo4j?
Yeah, Neo4j is a pure graph database system. This is more broad. So it's not a pure graph database system. That means Neo4j has optimized the structure for performing graph queries. Here, you can actually think of it as a general data management system, which offers more customized options for graph data. But it's more broad than a graph database system. Of course, we can compare and we have benchmarks against Neo4j and Tiger Graph and other graph database systems. but relational AI is more broad than just being a graph database system. And people think of it as such, and part of my interest in joining and being involved came from graphs, but in reality, it's a way more broad system, and many customers actually use it for data that have nothing to do with graphs. For example, I was mentioning tax because people care a lot about this rule-based reasoning. So let's go back to the slides. As I said, there's a lot of material, but I really enjoy this interaction. So just a reminder for those who don't remember a join. So basically, you can have two relations. Think of it as two tables here with a common attribute. So you may have employees that work in a specific department ID, and you have the mapping of each ID to the name of the department. So if you join on the common attribute of department ID, and you get the result that you see on the bottom of the slide. So this is an inner join, and by default, I'll be talking when I say join, it will be an inner join. And now I would like to move to, here's the pointer, to the more graph theoretic background. As I said, please, if you tell me we know this stuff, we saw it from Ioana or whatever, I can just skip that. But it's like the notation. So we have a graph. A graph consists of a set of vertices and a set of edges. The set of edges is a subset of the Cartesian product of the vertices. So basically, it's two node IDs, okay? It can be a set if the graph is undirected, or it can be a tuple if the graph is directed. Frequently, we abuse a notation and we put a tuple. So we notate UV as an edge, and we understand from the context if it's undirected or directed. So the degree of a node is simply the number of its neighbors, and we will use at some point, probably, if I get to be a bit more technical later, the degree of a node within a set. So basically, it's a number of neighbors of U within that set. You can be in that set, can be outside, we don't care, okay? Now, if we have two sets of vertices, they could be even the same. They could be having overlaps, they could be disjoint, doesn't matter. So you have two arbitrary sets. The set of edges ES, T is the edges whose one endpoint lies in S and the other endpoint lies in T. Okay, so if S is equal to T, then basically we look the set of induced edges. So I give you a set of nodes, how many edges exist within that set? And typically I use this notation, little e of S to be the cardinality of the number of induced edges. So the graph cut in general is defined by a set of vertices. So I give you a set of vertices, maybe a set of you here, and within a social network, this defines a partition of the social network to this set of students who attend this venue compared to the rest of the social network. This is a cut. And naturally, we have the edges between S and the complement of S. So basically, the rest of the nodes, I use this notation for the complement. And this notation I use for the induced subgraph. And we will also be discussing about triangles. So the induced triangles are the triangles. So you have three edges, and all the endpoints are within the set S. Okay. This is a bit boring, but it's necessary. So to set up the notation, the average degree is what? It's the number of edges times 2 divided by the cardinality of the set. May I ask why do we have the number 2 here? If we talk about the average degree, just to make sure everybody is paying attention. So I said the average degree. So what is average degree? It's the sum of the degrees divided by the number of nodes, right? So the sum of the degrees is simply 2 times the number of edges. Why? Yes?
Because when you have an undirected graph, it takes into account both.
Exactly.
Both ends of the.
Exactly. So an edge contributes one to one of its endpoints and another one to the other endpoint. So basically, when I sum the degrees, I just take 2 times the number of edges. Okay. So this is average degree. And if something like what I just said is not clear, just tell me why is it average degree? So sometimes because we think about optimizing objectives, and I may want to find the set that has the maximum average degree, 2 doesn't matter, so I may drop 2 because it's a constant. And I use this notation for just this ratio, okay? I call it average degree or degree density from now. You have also the edge ratio. So it's the number of induced edges divided by S choose 2. So this number, what range of values does it take? Clearly, it's positive because all the entities involved are positive. Can it be equal to 2 or 3 or 5 or 1.1? So if you have a set S that has 10 nodes, what is the maximum number of edges you can have? 10, choose 2. So this number here, you can think of it as a probability. That if I take a random pair of nodes, what's the probability they're connected by an edge? So it's a number between 0 and 1. And we also have the triangle density, which is a number of induced triangles divided by the cardinality of the set, and the triangle ratio, which is again a probability that 3 nodes randomly chosen form a triangle. Is that clear? Okay. Let me, I like asking questions, so I hope that's fine to keep you. So if I have a graph and I ask you maximize the edge ratio, find me the subgraph S that maximizes the graph ratio, the edge ratio. I claim that this is a trivial question. Why? That you can, yes?
No.
Ah, okay. So we said that this number is between 0 and 1, okay? If you take a single edge, what is the value of this subset? You have like 2 nodes. So you have 1 edge. So you have 1 divided by 2, choose 2. So it's 1 by 1. So even a single edge maximizes this ratio. So optimizing this objective doesn't make sense. However, maximizing this makes sense. So yeah, it's 0 if the set has no edges, which we call in graph theory independent set, and 1 if it's a clique. And here is the degree density as an example. Let's say this is my graph. If my set S consists of those 5 nodes, then I have 6 edges from the clique plus 1, 7. So I have 7 in the numerator. You can actually notice that those 3 edges are not counted because they're not induced. One endpoint is inside and the other outside. So we have 5 nodes, so it's 7 over 5. Oops. Okay, now we get to a little bit more complex concept, but it's very closely connected to the maximum average degree. So it's called the arboricity of the graph, which is the minimum number of forests needed to cover all the edges in the graph. The way I like to think about this concept is as a coloring concept. So I give you a palette of colors, and I ask you to basically color the edges so that there will be no cycle which has the same color, which will be monochromatic. So there is a theorem by Nash-Williams that actually proved that this value is actually an optimization of the number of edges induced by S divided by S minus 1. So very similar to the degree density. Of course, we restrict S to have at least 2 nodes. And basically, as an exercise, you can try to prove, to show that these two are basically very closely connected, okay? So I'll say that basically C2 and C1 are equal to 1, and they can differ only by a constant, which is, I'll let you try it as an exercise. Any questions so far? I know it's a lot of concepts and you haven't seen the connections.
Use the
You'll see, we'll get to this.
We'll get to it.
Yeah, for example, when you do triangle counting, exact triangle counting, the complexity of a famous algorithm of Chiba-Nishizeki is m, where m is the number of edges, times the arboricity of the graph. So instead of doing n cubed, you can do something better. And the key idea there is basically when you take the intersection of neighborhoods, you look, you order them by the degree, so you're careful about how you intersect.
So you use these theoretical results to estimate the planned time.
Yeah. So basically, this is part of the background. So these concepts will appear in the rest of the presentation. So I just want to set up the concepts. So graph theoretic concept, as we said, the size of the cut. Since we're talking about unweighted, undirected graphs, if it's weighted instead of an indicator variable here, you would have the weight. But basically, what this is the number of edges across the cut. For example, if you have this graph, this cut S comma S bar is summed over all pairs of nodes, where U is in S in this, let's say, part, V is in S bar, the complement, of whether they form an edge. So the only pairs that form an edge is this one and this one. So the cut of this partition is equal to 2. And a famous graph theoretic problem in CLRS, like in undergraduate algorithms, is the minimum ST cut problem. So I give you a graph, a flow network actually. You have S, let's say graph, for simplicity, you have S and you have T, and you want to find a partition where S is separated from T, and you cut the smallest number of edges. This was originally designed in the context of sabotaging railroads in USSR. If you want to disconnect the network and you want to inflict the minimum possible damage, how do you do it? Minimum ST cut, okay? Okay, and in general, if you take all pairs and you find the minimum, you can find the global min cut in polynomial time. And the reason why I say polynomial time is because we can solve this using a maximum flow. I suppose you're all familiar with max flows, so I won't go there. But if not, then the Wikipedia article or any standard textbook will give you the details. Now, another important concept, which goes beyond the density inside the set, is the conductance of a node set. So here we have a fraction, which is basically the number of edges that go from S to S bar divided by the minimum of the volume of S or its complement, where the volume of S is simply the sum of the degrees inside the set. Now, if you see this, you can get quickly an intuition what this means. So basically, this ratio is going to be low if the numerator is low and the denominator is large. When does this happen? When you have few edges going outside the set and many edges inside the set. So this captures well the concept of a community. Okay, a community is a set of nodes, loosely speaking, that they're well connected inside, but less well connected to the outside. For example, if you say, take here in Nicosia a group of chess players and you look their connections compared to the rest of the network, they will be more densely connected. And this allows us to mathematically find in an unsupervised way sets of nodes that have similar interests, potentially, assuming that when you have similar interests, you're more likely to connect, okay? Which is a reasonable assumption. There is a probabilistic interpretation of this. I just want to say that this number also is between 0 and 1, where basically you can think that you do a random walk starting from a node chosen from S with probability proportional to its degree and looking what's the probability that after one step it will go out. So it has also a probabilistic interpretation. Okay, so think of it as an escape probability. If you're a community, the probability that if you randomly walk around this community, you'll stay inside is higher. The minimum over all sets of the conductance is called the graph conductance, which basically is going to be low when you have communities. So if this is low, intuitively you have at least one community in the graph. And if this is large, we call these graphs expander graphs. And these are very important objects in pseudo-randomness, in graph theory, and in many other applications. Now, matrix vector multiplication, I'll try to go a bit faster because you're all familiar with this, but given a matrix, square matrix n times n and a vector x, then you can multiply a times x and you get a vector y, where the coordinate of y is the dot product of the ith row with x. And the key thing that you need to remember about the matrix vector multiplication is that the runtime is proportional to the number of non-zeros inside A. So if the matrix A has m non-zeros, basically we can do it in n plus m time. This is what I want you to remember. Matrix vector multiplication is efficient, but when you do matrix multiplication, because you have n such matrix vector multiplications, if you do it in the straightforward way, it's a cubic operation. There exist some ingenious algorithms. The first one by Strassen that gave an n to the 2.81 algorithm. Here, the computational model is the standard RAM model, okay? So I suppose you're all familiar with the big O notation. Okay, great. And there's a lot of effort in reducing this exponent. Currently, the best result is from Allman and Williams from MIT, and its value is less than 2.37. And the best lower bound that we have is n squared in reality, which is a trivial lower bound. Okay, eigenvalues play an important role. So just a reminder, lambda is an eigenvalue with eigenvector x if m times x is equal to lambda x. And one important theorem is that if M is a symmetric matrix, then M has a spectrum. Spectrum will mean the eigenvalues, lambda 1, lambda n, which are all real. In theory, this doesn't have to be the case. You can have complex eigenvalues. But if it's symmetric, which happens in the case of undirected graphs, when we think of them as matrices, as we will see later, then basically you have real eigenvalues. You can diagonalize the matrix using the eigenvectors and the eigenvalues. So M is equal to X lambda X transpose. And you can also express this multiplication as the sum of n rank 1 matrices. So xi times xi transpose, this is a vector times a vector, right? So this has dimensions n times 1, and this is 1 times n. So this xi times xi transpose is a square matrix. And because xi is a vector, this has rank 1. So basically, you can decompose your matrix M into the sum of rank 1 matrices. And frequently, what happens, why do we care about this? Why do I give you all this stuff? Is because an idea that you may find useful is that you can do low rank approximations. PCA, for example. Are you familiar with principal component analysis? PCA, have you heard of it? It's a very important tool in data analytics, okay, in general. What is the idea? You find a low rank approximation of your matrix that keeps most of the variance in your data, and it reveals a lot of structure. So this is a reminder. Okay, now if we have a graph, we can associate different matrices to it. For example, if I have this little graph, I have the adjacency matrix, which puts a 1 in the ijth entry if I and j are connected by an edge. So conveniently, the nodes are numbered 1, 2, 3, 4, corresponding to the rows. So you can see that 1 is connected to everybody. So 1 is connected to 2, 3, and 4. Node 2, however, is connected only to 3 and 1. So you can see it's connected to 1, because here you have the first column. It's not connected to itself, so we don't have a loop. There exist graphs where we have loops. It's connected to 3, so we have another 1. And it's not connected to 4, so you have a 0 here. Is this clear? Good. It can encode, of course, directed graphs as well in a similar way. And now here's an important graph, which is called the Laplacian of the graph. May I ask, how many of you have seen Laplacian before? Okay, only a few. Okay, so there is, so this is another matrix representation with different properties from the adjacency matrix. So this is a matrix where in the diagonal of the matrix, you have the degrees of the nodes. So you can see node 1 has degree 3, node 2 and 3 have degree 2, and node 4 has degree 1. And then if the off diagonals, you have the opposite of the adjacency matrix. So basically, wherever you have 1, you have -1. So you can actually see that the sum of the rows is equal to 0. That means if I multiply this matrix with the all ones vector, I will get the 0 vector, which means that, going back to the previous slide, that 0 is an eigenvalue with eigenvector all ones, just to make a connection between the two. Why? Because, as you can see, the sum is equal to 0. So this equivalent, if I hit this matrix with a vector which is all ones, I will get 0. 0 is like 0 times all ones. So the Laplacian always has an eigenvalue of 0 associated with an eigenvector of ones. And it has another magical property. Let me tell it to you now. If you look, the multiplicity of eigenvalue 0, it's equal to the number of its connected components. So if this graph, if I had, let's say, nodes 5 and 6 here, okay, connected by an edge, so the whole graph had 2 connected components, then the eigenvalue 0 would appear with multiplicity 0. Okay? So this is a property of the Laplacian that one can prove as an exercise. Another important property of the Laplacian is that if you take a vector x, which is binary, and you look the multiplication x transpose Lx, then this is a quadratic form, which basically is the sum over all edges of the square difference of the values of the endpoints of the edge. Now, I would like to emphasize that this is a very important expression. Why? In semi-supervised learning, you may want to say, you may have some labels, binary, let's say, and these labels are fixed, and you're trying to infer the labels from the other nodes. A classic paper by Lafferty and Garamani and others, Zhu, Garamani, and Lafferty, actually tries to minimize this objective. So think of X as being values on the nodes, which are classification labels, and then you say, I want to minimize this quadratic form in the sense that if two nodes are close by in the graph, they should have similar label. Okay? So this can be the objective and has been the objective of semi-supervised learning, where I give you a small subset of labeled nodes and you want to infer the rest. You find the vector x, which minimizes this expression, subject to fixing the nodes that I give you. Furthermore, it has another interpretation that if you think of a resistor network, resistances, okay, and you think of it as a network where basically you add a weight to the edge equal to the inverse of the resistance, this expression is equal to the amount of energy the network burns. So if you're familiar with electrical engineering, this comes up all the time. It's exactly the sum, the energy that the network burns. Why? Because X will correspond to the vector of voltages in the points, in the nodes. So here you will get the difference of the voltages. So in our context, when X is binary, and you think about what happens when you have a binary vector, well, you can have 0, 0, 0, 1, or 1, 1. So the only non-zero terms are going to be for nodes that have value 0 and value 1. So if I think of X as encoding a cut into two sets of the graph, this expression will conveniently give me the number of edges that go across the cut. It has also this property. So for example, if I set node 1 and 4 to be 1, and I think of these two nodes as one set, and those two as 0, then X transpose Lx is going to be equal to 2. Why? Because of these two edges. It's going to be equal to those two edges, because these will be the only ones contributing to this quadratic expression. Any question? Yes, thank you.
Send it to multicast with only one cut.
Very good question. Well, you can extend multicuts as a set of one versus the rest, but it doesn't expand. Then you need to have to every node not just a value but a vector. So then you go from quadratic optimization to something called SDPs. Yeah. So there exist semi-definite programming approaches to encoding multicuts, but it's here we just have a value. We have a number. So it's so what I'm trying to show you is that through this simple mathematical expression, I've made connections to machine learning, classic machine learning, graph semi-supervised learning, to electrical engineering, and it goes even to deep learning when we talk about GNNs with personalized PageRank and so on. There exists another matrix which is normalized, where basically we have ones in the diagonal. So we don't let, especially when you have graphs with very skewed degree distributions, you may want to normalize the degrees. And in the off diagonals, you have -1 divided by the square root of the product of the degrees for every edge, otherwise 0. This is called the normalized Laplacian. And why is it very important? It's super closely connected to a random walk matrix. So what is a random walk? Think that you are a random surfer. You start from some node, let's say 1. And then when you're at node 1, you choose one of the neighbors of 1 with uniform distribution. So I start from 1, and let's say I decide to go to 4. Then at 4, I choose one of the neighbors, again with uniform distribution. But since I have only one neighbor, I go back to 1. Maybe then I choose 2. So this creates a random trajectory, which is encoded by this Markov matrix. So basically, you can see if you're at node 1, let's say row 1, you go to 4 with probability 1/3, 2 with 1/3, and 3 with 1/3. However, when you are at 2, you can go to 1 and 3 with probability 1/2, 1/2. Basically, the PageRank is a stationary distribution, is an eigenvector of this matrix. So what you know as PageRank is an eigenvector of this matrix. Okay. I say basically because it's a bit more complicated. The graph is directed, and you want to ensure that if you go to a node, you don't stay there, that the distribution is well defined. So there you have this teleportation parameter of PageRank, but basically it's a random walk stationary distribution, which is an eigenvector. So why does a random walk have real eigenvalues? I claim it has real eigenvalues because if you remember from linear algebra, there is something called similarity transformation. So if I multiply it on the left by the square root of the inverse of the degrees times the square root of the degrees, so this is similarity transformation, I get exactly the Laplacian. So basically, since this has real eigenvalues because it's symmetric, and we have a similarity transformation, P is also having real eigenvalues. And there's a one-to-one mapping between those eigenvalues. So this is a reminder from linear algebra. If you haven't seen this before, we call A and B similar if you have an invertible matrix S such that this holds. So S times B times the inverse of S is equal to A. And when this holds, these matrices have the same eigenvalues. Okay. So a walk in general, not necessarily a random walk, is what you can actually see here is a sequence of nodes that have to be connected by an edge. So you go from U0 to U1, U2, and so on. These are nodes in the graph, and there has to be an edge between those two for the walk to be valid. And a walk is closed if you start from a node and you end up back to the same node. So if I start at 2, go to 3, back to 2, then to 3, then to 2, then it's a closed because I stopped exactly where I started from. This subset is also, this prefix is also closed to walk. And here I'm getting close to the end of the background, but basically I hope these concepts are very important and very foundational, and they play an important role in the practice of graph algorithms. So a very important inequality is Chigger's inequality. So basically, if you take the spectrum of the Laplacian matrix, either the unnormalized or the normalized one, you can connect the conductance of the graph to the second eigenvalue of this matrix. I would like to give you the intuition, because this is very technical, but I would like you to understand what is the key intuition behind. So if you have the Laplacian, the number of connected components, as I said before, is equal to the multiplicity of the zero eigenvalue. So if you see the zero eigenvalue appearing 5 times, it means you have 5 connected components, okay? This inequality encodes the following intuition. Let's say you have a connected graph, so the multiplicity of 0 is 1, okay? Just for simplicity. If the second eigenvalue is very close to 0, it means you can easily disconnect the graph. So it generalizes the intuition that the multiplicity of 0 gives you the number of connected components, which means they're totally disconnected. You don't need to do anything. But if you have a connected graph and you look the second eigenvalue, which is non-zero, the closer to 0, the easier you can disconnect the graph. And I won't insist on this really foundational inequality, which is a cornerstone of spectral graph theory, but I'd like to tell you that this inequality can be proved constructively. You take the second eigenvector corresponding to the smallest non-zero eigenvalue, you sort the entries of the eigenvector, essentially every node gets a value. You can think of the eigenvector as assigning to each node a value. You sort them, and then you do a scan. And for each subset of the nodes, prefix subset, you compute the conductance, and you output the smallest conductance. And the previous inequality states that the conductance of the graph is going to be not far away from the optimal conductance because of the previous inequality. Now, in practice, frequently, instead of finding only one smallest eigenvector, we'll find k smallest eigenvectors. So we take the Laplacian, we compute the k smallest eigenvectors, which we can do efficiently. We don't need to compute all of them. There is a way to just get the k smallest without doing all n of them. We take those as a matrix, and then we apply k-means on the rows of this matrix. So what I would like you to think is the eigenvector as assigning to each node a value. So if you have k eigenvectors, every node gets a vector of dimension k, which is the row of this matrix. So when you perform k-means, you cluster the embedding of the nodes. So this is your first connection to the concept of embeddings that we've been discussing in deep learning. This is like one of the precursors of node embeddings with provable guarantees. For example, in computer vision, and these are two classic papers, and machine learning, you can see this paper by Shi and Malik and Andrew Ng. They use spectral, they use this algorithm, they use this algorithm to partition images. So you take this image, you take this grid, essentially, you take this image, you create a graph by connecting each pixel to its neighbors, and you add weights on the edges, depending on how similar the pixels are. You can look the RGB, let's say, composition of each pixel, and basically, pixels that have similar coloring, they will be connected with a higher weight. So when you take this graph, which is a grid graph, and you do this algorithm that I told you on the previous slide, and you do k-means on this matrix that we got from here, you get something like this, which it's not perfect, but it captures the structure of the image. So I would like to take a small break because I think it's a lot, and I'm sure you have some questions. So any questions about this algorithm? Do you understand how you, yes, please.
Can you explain one more time why this is so related to node embedding?
Yes, so what is a node embedding? A node embedding is a mapping of a node to a d-dimensional space. So this matrix V over here, you can think of it as a node embedding. Every node is assigned to k coordinates. So it's a node embedding. And what is this node embedding capturing? I can continue telling you a lot about this Laplacian. It has, as I said, it's like the key object in spectral graph theory. But if somebody has physics background, they can also see it from another perspective of springs. Essentially, you can think of those edges instead of resistors. I'm electrical engineer, so I think about resistors, but physicists think about springs, right? So if you have nodes connecting with a stiff spring, okay, versus a more loose spring, and you think about this as your graph structure, so you have springs instead of resistors, and you let this system vibrate, the set of nodes that are connected with the stiff ones, this community, will vibrate together. Okay, so this is what you cut them, you cut it out. And this is what it's doing. So it's a node embedding. So these pixels get mapped to some part of the space and they're well separated from the rest. So it can cut it.
They get mapped together because they have similar
eigenvalues. Not eigenvalues, eigenvectors.
Eigenvectors, sorry.
So the values, so this is like, I wish I had a pen here, but basically you can think, the eigenvector has n values, right? One eigenvector has so think that each node gets some value, okay? From one eigenvector. Now you have k of them. So if you look the rows of the similar nodes, they will be very close to each other. So they get similar values from the eigenvector. And not only they get similar values, they're assigned in such way that you will be able to separate them by cutting few edges, or the weight of the edges, if it's weighted, the cut is the sum of the weights, is low. So this is a first machine learning which puts together, like if you see those papers, they have many tens of thousands of citations. They're very class papers coming from, this is from New Rips, back then it was called NIPS, from 2001, and this one from computer vision. So two separate communities back then, and they both used the same idea, spectral clustering.
Lena is prohibited meanwhile.
Yeah, it's a bit taboo now, right? Yeah.
The
Exactly.
usage of maybe.
Yeah. Well, I put just a face. Okay. So sounds good. Okay.
It's a picture that appears in every
Computer vision.
computer vision.
Yeah. So the last concept I would like to discuss is the concept of a spectral of a graph sparsifier. So I may give you a network G, and one task is, with respect to what you want to do, find a much smaller graph, sparser, that is similar to the input with respect to triangle counts, or maybe the density subgraph, or maybe spectral properties. Okay, so these are called triangle sparsifiers, density subgraph sparsifiers, and spectral sparsifiers. And this concept is useful besides the fact that it's super important in math, in pure math, in practice, because you can get faster algorithms on large graphs, you can get scalable machine learning. So if you, especially with GNN, scalability is a big issue. So if you can prove that when you sparsify in a certain way, you will still get the same output or something very close to that, great, you will scale up, okay? Efficient network monitoring, graph visualization, streaming algorithms, it's a very important technique. If you have limited memory, so basically the streaming setting is where your memory is very limited and you cannot keep a lot of information. So if you sparsify and your sketch, this sample that you have contains information you care about, that's great. And privacy preserving data release. So all the concepts I've discussed so far, they may look theoretical. My background is applied graph algorithms. So if you want to be doing applied graph algorithms, theory is needed. For example, if you design a randomized algorithm for, let's say, simple triangle counting, you need to prove how much you can sparsify so that you can guarantee that your output is close to the reality. And this is where math comes from. So you can, I hope today, and I'm not going to rush, I see I'm going a bit slow, but I really enjoy the interaction, and please ask me more questions. I don't want you to get lost in the math. And I'll show you some demos, is to make even few of the algorithms intuitive to you. So basically, how do you get a massive graph and count the triangles there very fast with guarantees? So let's get there. And the last part is random graphs. So
the question, what is the corporate, the big idea there? Is this, you use this as bounds, basically, these theorems,
yeah.
for estimating how to solve these graph problems that would require maybe quadratic complexity that you want to avoid.
Yeah,
that's the point.
Yeah, even you may even want to go to sublinear, depending on your computation model, because you may say you have to read your input, so you need linear always. But basically, you want to have speedups in general with high quality estimates, and in some cases, you want to have objectives based on them, like in machine learning. So, as I mentioned with Laplacians. So,
but would you care, like, distinguish? And I'm trying to think from the query processing optimization perspective, with whether it's a dense graph or a sparse graph.
For example, if you think about the query optimizer, it would try to do the joins based on the degree of the nodes. So it would say if it's let's say a node that has degree more than square root of m, where m is a number of edges, instead of looking the pairs of neighbors, I would look the set of edges. Because if you have more than square root of m neighbors, and you look pairs, you will get omega of m pairs of nodes. Whereas if you take this node versus edges, you have m exactly. So you can.
So in the database system, it would have been a catalog, though, I would say, and then you have.
Yes, I'll get there. I'll try to get there. So many of you have heard. Yes, please. What's your name? Nico. Yeah.
When so let's say I do sparsification on the graph, and my goal is that I create a new graph.
Yeah.
That has the same output, or I approximate really well the output on a reduced.
Yeah.
So, but the way I will do the sparsification matters, because
of course.
So if I do a triangle, I don't remember what it was.
Yeah.
Maybe some algorithms, when I run them in my sparse graph, they produce wrong ones.
Yeah, you have to do it with respect to a task. Okay, so if you want to find communities, you want to speed up this task. So you will give a subset of sometimes, most of the times it's a subset of your input graph, using some sampling or some type of approach. Typically, you may have also edges that don't exist, but this is not so frequent. So you will use it for this task to speed up your task. You cannot go and use it, for example, if you do uniform sampling and you care about cut preservation, you may fail, right? Because if you have like 2 clicks connected by an edge, this edge will fail if you do uniform sampling. You need to do some other form of sampling for that. Okay, this is why we have not one sparsifier for everything, we have per task. Okay, so random graphs and in general generative models, which is something you hear a lot in deep learning. How do you generate graphs that are molecules that are potentially targets for drug discovery and so on? Essentially, what we have is a probability distribution over topologies of graphs, and we're trying to learn this from data. But from a pure math perspective, a random graph a graph is never random, right? What we mean is a probability distribution associated with a graph. So maybe I have this collection of 3 graphs and I assign uniform distribution. This is a random graph model. So if I have this specific graph and I say it's a random graph, while it's not random, it means it was sampled from this distribution. Okay. Who invented this term? Erdos and Rainey pioneered the random graph model. Also Gilbert, but these were the ones who did the very hard math work. So the model that you will hear during this talk is the GNP model, where n is a number of nodes and p is a probability of an edge. So how do you generate this? For every pair of nodes, you generate the edge with probability p. So if you look any specific graph with m edges, doesn't matter which one, the probability it gets assigned is p to the power of m times 1 minus p to the power of n choose 2 minus m. Can someone explain me this expression? Just to make sure you understand this simple. So the edges are independent. So if you see the specific graph and you look every pair of nodes, if it's an edge, it appears with probability p. So it's p times p times p m times, and then for every non-edge, it's 1 minus p. And because you have n choose 2 minus m non-edges, this is the probability of any specific graph. So there exists another model which fixes a number of edges, but we won't be discussing about it. Okay, so now let's start with a very simple query, and let's see how this, like anybody can say, I can count triangles, I can take every triple, and I can check if there is a triangle, and I'm done. How this super simple problem combines so much machinery, even from topology in some way. I'll explain what I mean. So the triangle query in general in a database system is, let's say you have 3 tables, R, S, and T, where R has attributes A, B, table S has attributes B and C, and T has attributes A and C. I want to find all tuples A, B, C such that A, B appears in this relation, BC appears in table S, and AC appears in table T. This is a triangle query. Okay? Is this clear? Okay. Question. I was talking about triangles in graphs. How would you express the triangle problem in a graph using this triangle query from databases? What would be the tables? Well, if you think about it, a triangle means I have an edge, let's call it UV, then I must have another edge, VW, and then I must have another edge, WU. So basically, in the case of graphs, the tables R, S, and T is the same table, the set of edges in the graph. Okay? So this is exactly what this slide shows, that if we think about the edges as a database table with 2 columns, U and V, and for simplicity, let's say each row corresponds to an undirected edge, where U is less than V, we can express the set of triangles in the graph as this 3-way join. So I join the table with itself, and this is the question that one of your colleagues earlier asked me about, that you may have multiple joins. Yeah, you may have, and may be necessary. In SQL, for example, you could write it like this. If I want to count triangles, I could say select count as triangle count, and then I do this join based on the endpoints of the edges. I have this square statement here simply because I don't want to count every triangle more than once. So I order the nodes U, V, W to be from smallest to larger. And in data log, you can actually express it as a conjunction in this way. So I want to find all tuples U, V, W, where UV is an edge, VW is an edge, WU is an edge, and U is less than V, and V is less than W. These are 2 queries that can actually give you the triangles in a graph. Now, here's one amazing result, which at first sight has nothing to do with triangle count. Think about, you have a 3-dimensional body, like this pointer here, okay? So I have different planes. I have the XY plane, I have the XZ plane, and the YZ plane. So if I take this body and I project it down, this 3D thing will become a 2D thing, right? And it has a surface. Suppose now I tell you, I don't show you the object, I don't show you the volume of the object, but I show you the 2D projection of this control on the floor, on this side and on this side. And I tell you this is how many square centimeters it is here, how many square centimeters it is here, and how many here. Question, how large can the volume be? This is quantified by an inequality called the Loomis-Whitney inequality. So this is a simplified form in terms of projection. So basically the volume of A is going to be at most the product of the surfaces square root. Okay, it's a non-trivial result to prove. Now, this result can be has a discrete version which becomes a triangle query. So if you think about the 3D object as being the set of tuples of triangles, and you think about the projections as projecting to the first two attributes or the other two attributes or the third set of two attributes, and I give you the projections, then the total number of triangles is at most the square root of the product of the cardinalities of the relations. It's a very beautiful result, right? So you see how such a simple thing connects to very deep mathematical results. And actually, in the case of triangles, where, as we said, R, S, and T is just a set of edges, you get that the total number of triangles in a graph with m edges is at most n to the 3/2, which happens when you have a clique. So one thing, as we said, we can express triangles in this way, but this is not a great way. We haven't solved the problem. And the reason is when you do joins, joins can be inefficient, especially if you go in more than one join. So there exist intermediate results. I haven't written them out, I left it as an exercise, but basically I have created 3 tables here where I want to do the 3-way join. Each one has 2n plus 1 tuples. So the first one has tuple A0, B0, A0, B1, A0, Bn, A0, B0, this is included here, but A1, B0, and so on and so forth. So you have 2n plus 1 tuples in each table. The output of the triangle join, you can easily verify. It's a simple exercise. I don't want to do it here, but it's linear in terms of the output. But if you try any pairwise join, you will generate n square intermediate tuples. So basically, if you try a SQL query with an unoptimized and with a standard binary join, it will be very inefficient because it will generate a huge intermediate result. And this is something that relational AI is able to do very efficiently. So it's able to provide this worst case optimal guarantees in the exact counting where you guarantee time which is very close, actually up to some logarithmic factors, 1 plus n plus n to the 3/2, which is a worst case output size. Now, another connection, triangles as matrix multiplication. So here's my claim. If you take the adjacency matrix of the graph, and you take the third power, or in general, if you take any power R of the adjacency matrix, and you look the UV entry, this is a number of walks from U to V of length R. Again, it's not hard to prove that, but think about it. If I want to count triangles, I will have to go to the third power, and I will have to go to U to the diagonal of this matrix. So I will have to look the third power of the adjacency matrix, look the diagonal. Why? Because the third power of the diagonal entry is going to be the number of closed walks of length 3, which have to be triangles, right? So the diagonal is going to give you essentially the count of triangles. Now, my question is, if you take the sum of the diagonal entries, which in linear algebra we call the trace, so the trace of a matrix is the sum of the diagonal entries, can someone tell me what is the trace of AQ? It's clearly a function of the triangles, as I said. But is it equal to the number of triangles? Is it 2 the number of triangles, or 4 or 10? What is the constant? Well, if you think about it, if you start from U, you can go from UVW or you can go UWV. So for every diagonal entry, you will count each triangle UVW 2 times. But then, if you look also the entry V and W, they have counted this triangle also 2 times. So it's 3 times 2, which shows that the sum of the diagonal matrix of A cubed is equal 6 times the number of triangles. So the 6 is because we count each triangle for each one of the endpoints of the triangle, and we count it 2 times from each node, because we can go this way or this way. If you take, yes, Dimitri, question?
No, well, stupid question, but the triangle counting is, I mean, is this important for topology analysis to see the wellness of a graph topology, right? Overall. But are you interested in these like overall or like for isolated islands in a graph? Is this like a subgraph computation or complete graph computation?
So for now, it's a complete.
For now, it's complete.
I wanted
But
to start-
because the complexity is already,
Yes.
high, we already see this, right?
Yes, but we're trying to reduce the complex. So for the exact counting, we see that we have these approaches, exact counting, using matrix multiplication, using 3-way joins, using, I'll show a couple of algorithms.
In
and I'll
your
show the
case, you have
randomized.
relations, and then it doesn't apply to all attributes as far as I understand, right? Maybe you have many triangles for, let's say, I don't know, the common interest, but maybe you don't have so much triangles on another
Yes,
relationship.
we'll get to this part later for the applications. So this is about the global count. I give you a graph and I just want a number. And the reason why this is very interesting is because through this very simple problem, you can actually see a wealth of algorithmic techniques. So my focus is on the techniques that come to such a simple problem. Is that clear?
Yeah.
Okay.
But can I add something? Maybe.
Yes.
So the question why the triangle are important?
Yes. Okay. So you ask more about the motivation.
I want to add something here,
Yes.
like for the social media and stuff, usually the things evolve in triangles. So that's why, I mean, this can be like one application of triangle.
There are so many applications of triangles, and I'm going to show a few of them later on. I'm focusing so far on the actual algorithmic techniques. Perhaps I should have given a bit more motivation, but actually, if you want standard thing when you have a graph is to give some descriptive analytics, and you want the clustering coefficients or the transitivity ratio. So this involves a global triangle count. And then there are more involved applications, and actually I have a few later on. But so far I'm trying to show algorithmic techniques. So, you have a graph, you want to compute the total number of triangles, what's the best thing you can do? So the naive cubic algorithm, as we said, is like check all 3 in the beginning, but you can do something that captures the matrix multiplication breakthroughs that we said before. So you don't need to do n cube because we can do matrix multiplication even faster. So you can see how matrix multiplication is a very important tool. However, in practice, we don't use it, okay? Because these algorithms, they're not so practical on the scale of the data sets we're dealing with. Plus, we want to do something more combinatorial, okay? And more memory efficient as well in certain cases. So the other one, very simple method is just as a baseline, take the vertex V and check the neighbors of V, U and W, and output the triangle UVW. Well, this complexity is you have n nodes, and the total number of pairs that you can have is the maximum degree squared. So this is another very simple, straightforward algorithm. Now, a less straightforward algorithm is basically the following: very simple to implement, yet the complexity becomes much tighter, especially in sparse graphs. So basically, you order the set of the nodes, you take node V, and you look so take a look. You start from the high degree nodes to the lowest degree nodes, and then you look intersections of neighborhoods, but you look at them in the way that the degree is ordered. So when you take the intersection, you do it as an efficient hash join. So instead of having this cubic algorithm or matrix multiplication, it turns out that the complexity is equal for every edge. You need to do work proportional to the minimum of the degrees of its endpoints. Okay, so basically this turns out to be at most the arboricity of the graph, which, as we said, relates to the density of the graph times the total number of edges. And one can prove that arboricity is never greater than square root m, which of course makes sense in the case of worst case optimal joints and Loomis-Whitney inequality that I discussed earlier. Now let's see another idea. Do we need to take a break or?
Yes.
Maybe 5 minutes to.
Actually, it's
If we have a break
it
or-
was 2:30 to 4, and
Yeah.
then we have 4 until 4:30 to 6.
Okay, so.
Yeah.
Okay, let me just finish this slide quickly. So we said that the total number of triangles is equal to the trace of a cubed divided by 6. Okay. Now, from the spectral properties of a symmetric matrix, we can prove that a cubed has eigenvalues of the original matrix to the cube. So if A has eigenvalue lambda 1, A cubed has eigenvalue lambda 1 cubed. It's very easy to prove. Okay. So the number of triangles is equal to the sum of the cubes of the eigenvalues. And this gives an eigentriangle sort of formula where you say that the total number of triangles in the graph is the sum of the cubes of eigenvalues divided by 6. And you can actually use the diagonalization of the adjacency matrix to actually get the triangle counts for every node. But now you need to involve the eigenvectors, and specifically this is a formula. So you sum over all nodes j of the ith coordinate of the jth eigenvector squared. So why is this important? Let me now show you how this simple idea, combined with all we said before, gets interpreted in practice. So here you can see the spectrum of a toy data set, and you can see the top eigenvalue is 74.08, the second one is 59.94, the third one is minus 29.36. They're sorted in terms of absolute value. And then you can actually see that the rest of the eigenvalues are almost symmetric around 0. What does this suggest to you? That maybe, since we take the sum of the cubes of the eigenvalues, if most of the eigenvalues are symmetric around 0, and just few of them are well detached from the rest, maybe if I take those few, I will get a good approximation. So let me show you something quickly. If you go to, let's see, demo notebook. So this is a simple algorithm, right? Eigentriangle estimate, it takes adjacency matrix, it takes the rank of approximation that you care about. So it computes the eigenvalues in a sparse way, so you don't need to compute all of them. You can just compute of them the small amount very efficiently using matrix vector multiplication. So this is an efficient step. And then you take the sum of those eigenvalues cubed and you divide by 6. And this is your estimate. So let's see how this works. So if you run it on a simple GMP graph, the exact count was 20,828,000 and so on. And this simple estimate using a single eigenvalue gave 20,944,000 and so on. So there is some error, but instead of computing n eigenvalues, we computed only one, and we got essentially the count. Now, why is this the case? Let me show you something. If you plot the spectrum of this adjacency matrix, the top eigenvalue is 500, and the rest are within this range. And as you can see, very importantly, this set of eigenvalues, they're almost symmetric around 0. So what happens is that this contributes a lot, much more, because it's 500 to the cube compared to the second, which is 42 to the cube. But way more importantly, 42.2 to the cube probably has another minus 42.1 to the cube. So somehow they cancel out. So this idea has been applied to many other data sets, and it has worked very well. So I have some very small network X data sets for you to experiment. But another very important product that this idea led to was to do graph mining using matrix vector multiplications. And this led to the CMU Pegasus project, which received an open source graph. Sorry, I don't know why today it's not.
Oh, yeah, well, can happen, unfortunately.
Maybe I'm not connected. No,
No, hold on. I'll let you know. It's
nothing.
firewall issues.
Yeah, okay.
We
So
have it,
basically you
but
can.
I can open a hotspot if you want to.
No, it's not so crucial. Like you can check it. It's Vega CMU. So basically, this idea of matrix vector multiplication that, as I said in the beginning, we can do very efficiently in practice, can be used for a variety of graph mining tasks. So you see how all the math and applied stuff, they can get translated to smart heuristics or algorithms that give very fast results on petascale graphs. Okay, so yeah, let me know when you want to have a break, but I can continue.
Yeah, I think we should have a break now,
Okay.
and then we continue.
Sounds
You
good.
know, yeah, just to be within the time. So 30 minutes, okay?
Should we stop the recording for a
Yes,
second?
yes, I will do that. Hold on.
Okay, so welcome back. So we were discussing about triangle counting. We saw a very simple idea, low rank approximation of adjacency matrix with appropriate formula can give you very accurate counts, both in the global setting where you care about the per node actually. So now I'll show you another algorithm, which is randomized procedure. And basically what it does, it takes the input graph and basically just tosses a coin for every single edge with probability P. So let's say P.1, you keep 10% of your edges randomly. You take the graph, the resulting sparser graph, G prime, you count the triangles there with any algorithm that you like, the ones we discussed, matrix multiplication, node iterator, whatever you want. And if T prime is the count of triangles in the sparse graph, then you return T prime divided by P cubed. This algorithm. So the claim is, if you choose P carefully, you can get very significant speedups while T uppercase is very close to the true triangle count. Why do we divide by P cubed? Well, if you think about the triangle in the original graph and the sampling procedure, the probability that this triangle, let's call it, survives the sampling process is when each one of those three edges survive. So they succeed. And this happens with probability P times P times P. So P cubed. So if you think about the expected value of this T prime, this random variable, is P cubed times T. So each triangle survives with probability P cubed. The triangles are not independent. However, there is a very important property in probability called linearity of expectation. So if you have the sum of variables, and you take the expectation of them, even if those variables are not independent, they are dependent, then the linearity of expectation tells you the expectation of the sum is the sum of the expectation. For the variance, this is not true, right? If you take the variance of x plus x, so x with itself, clearly there is no independence, then you will get 4 times the variance of x. Okay, so this property holds only for the expectation. I said something here that is this part clear? This expectation? Okay, excellent. So this output just rescales T prime so that in expectation we get the right count. So the question is, how do we choose P? Clearly, we can set P to be 1 and there is no sampling, okay? But our goal is to choose P as small as possible so that our output is very close to the true count T lowercase. This WHP stands for with high probability. With high probability means that as the size of the graph increases, the probability we get the correct answer goes to 1. So basically, it's 1 minus, let's say, 1 over n. So as n grows, this term goes to 0, okay? Is the algorithm clear? This is it. Let me show you very quickly on the notebook. So if you look, this algorithm, Doulion,
This notebook will be shared with participants.
It's on GitHub, so
It's on
everybody.
GitHub.
Yeah,
Okay,
yeah.
I took a note. I will share it with
Yep.
the slides.
Yeah, so here you can actually see this is a naive implementation, just a demo. You can do this much more efficiently. For every edge, you toss a random coin, and if a random coin gives you basically success, you add the edge to the sparsified graph. Now, one question I would like to hear is like, how can you do this more efficiently? So here is a question for you. Like, if I give you n trials, n coin tosses, and each coin toss has success, let's say 2 over n, how can you generate those coin tosses without tossing a coin for each time from 1 to n? There is a way to do that, but this gets into probabilistic generation. So what I mean is you can sample from a binomial distribution instead of linear time in sublinear time. So if you have, let's say, binomial random variable, n tosses with probability p, you don't need to toss a coin each one of the n times when p is very low. There is a smarter way to do that. And this is by generating geometric random variables. So if p is very low, you can prove that basically it's better to generate a geometric random variable that tells you when is the next success and so on. So basically you can do it in time proportional to the output where output is the number of success coin tosses. So this is the algorithm, very simple. And if you try it on some toy graphs, you can actually see very small. You can just illustrate the idea. This is a small graph, 50 nodes. Still, you can get 14.5, even if you keep 80% of the edges. And you can get in this Davis-Weyman graph, what was the probability? Yeah, it's quite high. Now, the question is, how small can it be? How small can P be and still get this high quality of estimates? And this is what I'm going to answer next. So this is exactly what I told you, that the edge sampling can be done in expected time P times M, where M is a number of edges. This is a classic problem in Donald Knuth's Art of Computer Programming. It's an exercise there. And this can be done, as I said, with geometric random variables. So this is left as an exercise. I won't do that. But basically what I want to show is that we can express a number of triangles T as a multivariate polynomial. So for every edge, I associate an indicator random variable xc, which is 1 if the edge succeeds to survive, and 0 otherwise. So then the total number of triangles is the sum over all triangles in the original graph, consisting of edges E, F, G, of the product of those indicator random variables. So a random variable is a polynomial. It's a cubic polynomial. And as I said, the expectation of this, given that we have linearity of expectation, is p cubed times t. But the variance, you cannot just take the sum of the variances of those things. Why? Because a very trivial way to see that is if you have 2 triangles that share one edge, the probability that they both survive is not p to the power of 6, it's p to the power of 5. So clearly you have dependencies in this sampling procedure. Okay, so when you try to understand the distribution, so think that t is a random variable, t uppercase is a random variable. What do we want to do with random variables? We want to understand their distributions. Sometimes it's too hard to understand the full distribution, but we may want to understand the expectation for sure, the variance, and maybe some higher order moments. So my point is that the distribution of this is not trivial. The mean is easy because of linearity of expectation. But then you need to think about this random variable. And actually, to analyze it, I used probabilistic concentration from multivariate polynomials. I won't show you because it will be even more technical. I decided to skip that, but I'll show you the theorem. It says that if you sample P at least to be the match of these quantities that I'm going to explain, then you are guaranteed that the output, which is a random variable, minus the expectation, which as we said is a true number of triangles, being greater than epsilon times the true count, is extremely small. It goes down to 0 extremely fast as the number of nodes grow. So what is these quantities? Delta is the maximum number of triangles that an edge is contained. This is always at most n minus 2. T is the number of triangles. and this tilde notation hides log n factors. So this is a theorem that quantifies how you need to check to set P to optimally get concentrated estimates. This result in math is called measure of concentration. Okay, so the probability that you're very close to the true expectation is very, very high. The probability you're far away is very, very low, conversely. Now, what is the problem with this expression here? From a practical perspective, it tells you how to set P optimally, but you don't know T, which is the number of triangles. And this is what you're trying to do. Of course, you can solve this in practice with a way I will explain, but the theorem, I just want to show you that it can justify, depending on the black box you use as your triangle counting algorithm, you can get provably speedups which are order n. So you may have a graph with 10 million nodes. You can actually justify order 10 million fold speedup. Okay? Depending on the graph. For example, for a graph that has more than n to the 3/2 triangles, then you can justify this speedup, even if delta is the worst case, which is order n. So there are many experiments. This method has actually been incorporated in many systems. Okay, like in many toolboxes, it's well known, and you can find more numbers. But these are some small graphs that you can see on the previous slide with, let's say, few million of edges. Orkut is the biggest one. So if you look Orkut, from 200 seconds, you go down to something like 5.6 seconds with an average error 0.6%. This is not 6%, it's 0.6%, okay? So less than 1% error. So it's very practical. And now let me show you how you can actually apply this algorithm in practice when you don't know the optimal P. What you do is you start with a small value of P, as small as you like, 1 over the number of nodes, okay? You run the experiment a few times, and you look if the output, the random variable output, is concentrated around the mean. Why? Because if we have chosen the right P, we know that this probability should hold. So if we repeat the experiment multiple times, the values should be very close to each other. So the key idea here is we do something like this. We start, just to illustrate, okay? We start from P.01 in this story example, 1 over 100. I run it 4 times. And I do see that the ratio, of course, you don't know T in practice, but you can actually see the counts, and you can compute the variance and the mean of the counts. If these numbers here are well concentrated around the mean, then you can say I'm stopping. If not, you double P. You go to 0.002, sorry. And you keep doubling, or you keep increasing in some way. So the point is that if you do this, while it looks inefficient, you can prove that the runtime will only introduce an extra logarithmic factor, total, log n, where n is the number of nodes. So you can probably start with a small value of P that won't give you good results, keep doubling it, and when your 5 experiments, 6 experiments, they all give close values, they're close, you can quantify this by looking the variance compared to the expectation squared. If this ratio is small, it means you're well concentrated, and then you stop. You say, I'm done. I deduce concentration, okay? Is this clear, how you could apply it in practice? Good. Okay, so now I talked about, you have a black box triangle count. This triangle count could be also approximate. So you can sparsify and then use an approximate method. So I'll try to go a bit faster through this because I want to get to some more practical stuff as well. But this is like a tour of different algorithmic techniques for such a simple problem. So another tool in randomized algorithms, which is being used all the time, is called Chernoff bound. So basically, you can think of it as the central limit theorem without giving you similar type of concentration for independent experiments. So one could say, here is a very simple algorithm to count triangles. I will sample triples, and I will check if the triples form a triangle. It turns out that if you sample n cubed log n divided by t times epsilon square triples, then you can guarantee an epsilon quality approximation. That means your output is going to be 1 plus minus epsilon times the true count. So you can actually see if t is very large, closer to n cubed, this is going to be very efficient. But for graphs that have less triangles than n cubed, this is not going to work very well. There is another idea. This goes to what Dimitris was asking about the query optimizer in the triangle query. So basically, the key idea is that you can have a hybrid sampling. So instead of looking at triples, or you can actually think, I take a node and I look at a pair of neighbors of that node, you can actually, for low degree nodes, sample pairs of neighbors. So you can compute the degree sequence. And if a node has degree less than square root of m, there is a reason why we have the square root of m. We pick neighbors. Whereas if it's a high degree, so it has degree greater than square root of m, I pick the node and a random edge. Why do we have this square root of m? Because if a node has square root of m degree, the number of pairs is upper bounded by order m. Okay, square root m squared. So in that sense, it makes sense to take basically a low degree node and a pair of neighbors. If you have a high degree node, let's say with degree greater than square root m, it doesn't make sense to take a pair of nodes because the number of pairs is greater than square root m squared. So in that sense, you take the node and the random edge because there are at most m edges, right? So in that sense, you balance those two, and it turns out that the number of u of triples is upper bounded by m to the 3/2. So this n cubed becomes m to the 3/2, and you can prove this via Chernoff-Mounts. So we had a hybrid strategy with Gary Miller, Kolontzakis, and Richard Peng, where basically we combine the sparsification together with hybrid sampling. And let me show you some results. These are some graphs, and you can actually see they have like up to Orkut is the greatest one. This paper is from more than a decade ago, yet it has been used also in the semi-streaming model. So basically, this is exact counts. Error is 0 because exact, and here are the runtimes. This is without sparsifying, so just triple sampling. So if you do this triple sampling, these are the runtimes, so you do see an improvement. If you do the hybrid, you can actually see that the time is more or less the same. It's a bit larger than here, but the error drops significantly. Now, if you combine the sparsification that we discussed before together with the sampling, you get really the best results. So for example, let's choose a big one. So the exact, let me check here. So this is the sparsification using exact on the sparsified graph. Okay, so you can actually see that if we take the sparsifier and then we use a node iterator, then we, in less than 10 seconds, with error 0.1%, we find the actual sum count. If you use a hybrid sampling, you can actually see that you get better runtimes and the error doesn't increase significantly. So basically, when you go to even larger data sets, we have pushed the performance to the best possible in the sense that you are sparsifying as much as you can and you're using approximate counting in a hybrid way to optimize the sampling on the approximate counting. And this is that paper that you can find in the references. Now, I would like to conclude this part by actually saying about the state-of-the-art algorithm, which I designed together with Rasmus Pei from University of Copenhagen. And this is probably the best algorithm, randomized algorithm you can get without any further assumptions. So here's the idea of this algorithm. Instead of tossing a coin for every edge, we're going to hash the nodes to colors. So think that I have a palette and I map every node to some color. Let's say we have C colors, 1 to C. You get a colorful graph, and then you will keep the edges whose endpoints have the same color. So if I set the number of colors to be 1 over P, so if I think of the inverse of the number of colors as a probability, in the sense that the more colors I use, the less edges I will have, because fewer will be monochromatic. What we do here is we keep the monochromatic edges, we count the triangles in this sparsified graph, and we scale t divided by p squared, or equivalently by the square of the number of colors. Now, why do we scale by the square? This sampling essentially, remember when I said that the triangle count is a multivariate polynomial of degree 3? We had the product of 3 indicator random variables. So this is a cubic polynomial. This lowers the degree of the polynomial to 2. How? Well, if you have a triangle, think for a moment, if this edge is monochromatic and this edge is monochromatic, what can you tell about the third edge? It's also monochromatic. So you don't need to toss another coin for that edge. So it introduces this dependent sampling. So basically what we improve from the previous guarantees is we had t to the 1/3. This becomes square root t. So I can sparsify even more. And this is state of the art. Okay, it has been used very widely. This part, I just want to outline that so far it has taken more, but I do hope that I have illustrated a wide variety of diverse algorithmic techniques, starting from spectrum, matrix multiplication, measure of probability, randomized algorithms, exact algorithms, and you can actually see how easy it is to implement these algorithms. The tough part in the papers is to analyze it. Okay, so these are the techniques, and feel free to take a look in the references. I have more papers, and these are some well-cited papers within this topic of triangle counting. So more papers have followed up in dynamic graphs, in streaming graphs, etc. Okay. So now I would like to talk about this unsupervised learning problem of finding clusters. But before I move there, let me take a quick pause and ask if you have any questions about the previous one. You can see some demo notebooks on the Git, similarly to what I showed so far. Anybody questions? If not,
so how are these operators being integrated in the relational AI stack you presented earlier?
Yes, one key thing that you notice is going from product release takes time. So some versions are in preview mode, let's say, but there are many systems that are using these approximate counting ideas to speed up counts of motifs. And this like what I showed is a triangle. Essentially, you can have a click, like a K click, a 10 click. You may want to count 10 clicks. You may ask why. Actually, I had a collaboration with Harvard on brain networks, and they wanted to count higher order clicks, which is a very tough problem. And this idea actually is even better, right? The colorful triangle counting, because a 10 click has 10 choose 2 edges, 45 edges. So if you toss coins for each one, you have p to the 45. But if you do the colorful counting, you reduce this degree by a lot, right? It goes linear to the number of nodes. So you can sparsify much more. And they care a lot about the brain structure, understanding how things evolve with time in connectivity and so on. And we talk about experiments that may run for months in this realm. So I had the collaboration with Hans Pfister from Harvard, and our experiments were running for months, actually. And you see where these algorithms actually play an important role as well. Okay, cluster detection. So I'll start with the density subgraph problem, which I mentioned, is the subgraph that maximizes the average degree. So when we have n nodes, how many subgraphs exist? 2 to the power of n, right? For every possible subset, we have an average degree. I want to find a subset that gives me the maximum degree. Some people think at first that this should be NP-hard, but turns out it's a very nice application of max flow. So it's not an obvious thing. So I'll try to guide you through some of the intuition, even if there is some algebra involved. So basically, we have this graph, and instead of trying to maximize the degree, I will try first to be able to answer whether there exists a set S with average degree at least C. Why is this a natural step? Because if I think about the average degree, it goes from 0 to n minus 1. 0 if it's empty graph, n minus 1 if it's a click, right? So there is a range of values of the average degree. So then potentially I can do binary search on the average degree assuming there is some monotonicity, which exists, and query this a logarithmic number of times, log n times, for different values of c. If the query tells me, yes, there exists, I can go above my query c. I can increase my threshold. If it tells me that no set exists, I need to decrease my threshold. So basically binary search on C, okay? So let's see whether we can actually answer this query. The answer is yes. We create a flow network, we add S, we add T. So these are nodes outside my graph. And we reduce a problem to whether there is a cut smaller than a certain value. And if you do the algebra, which we can do, but basically, if you follow the steps, it's straightforward. You take this inequality, and by simple steps, relying on properties of the degrees and the fact that we have a cut S complement, it reduces to this expression. The sum of the degrees of the nodes U in the complement of S plus the size of the cut plus the cardinality of S times C, which is a query threshold, is at most 2 times the number of edges. You can do the algebra, but trust me, this is the last step. So now I can answer this by doing a minimum ST min cut computation, which is a max flow computation. So basically, you can actually see that if I create a flow network, where S is connected to the nodes of the original graph with edges of capacity equal to the degree. I suppose you're familiar with max flows. I didn't want to go into that background as well. But if not, you can refresh your memory by looking at Wikipedia. So edges have capacities, and you allow flow to go from S to T, right? The flow along an edge can never exceed the capacity, and you want to maximize the flow from S to T. So the edges here get capacity 1. The edges from S to the nodes of the graph get capacity, the degree of the node. And the edges from the nodes of the graph to the destination T are equal to the threshold value C. So we take our input graph G and we create this flow network. Yes.
How do you decide what like the source and the sink of the
Yes.
graph, what edges they get? Because some of them are connected to the nodes of the graph and some.
Yes, no, all of them are connected. So I create 2 new nodes, S and T, okay?
You just let them out.
Yeah, they don't fit. Yeah, sorry. Yeah, I put the dots here.
Yeah,
So
okay.
yeah, sorry, yeah, this one. Okay, so basically S is connected to every node of the graph with a capacity equal to the degree. And from every node of the graph to the destination with capacity C. And all the nodes, all the edges here get capacity 1. So the construction is straightforward. Of course, think about it, take some time. You need to, Goldberg came up with this a very nice idea. And basically, you can always observe that if you sum the degrees, you get a cut of value 2 times the number of edges, because we said the sum of the degrees is 2 times the number of edges. So if we set S to be empty, so what I said, this S refers to the subset from the graph that we care about. In an ST cut, this node little s is always separated from T. The question is, when we separate the little s from T, whether some nodes from the graph will go on this side. And this set of nodes, I call uppercase S. So basically, here's the algorithm. You create this flow network, you run max flow, and the nodes on the S side of the cut, if they exist from the graph, then you say, yes, there exists such a set. If little s is alone in the cut, then you say there is no such set in my graph. So this is the answer. So basically, if you take a subset of nodes S from the graph, along with, of course, the little s, which is the ST min cut problem, if you have this being the min cut, then you can actually verify that the value of the cut is equal exactly to this expression. Why? Because you have C capacity from those nodes in S, so you get this term. You have, of course, the sum of the capacities of the edges cut, which is exactly this, the number of edges times 1, and you get the sum of the degrees of the nodes in the complement from S to the complement. Is that clear? So you create a very smart flow network. You run max flow, and if you see that the little node S is separated from T without any nodes from the graph, then you say there exists no set in my graph that has degree greater than C. If you find one, you found one. This is algorithm. So we transform the graph into G, we find the min cut, and if, so as we said, the min cut is S with some nodes from my graph. If this S is empty, then we say no, but if S is no empty, then we return this as our output. And this is algorithm. So what did we do? We did one max flow computation to answer whether there exists a set of average degree greater or equal than C. By doing logarithmic number of them, we solved the densest subgraph problem. Exactly. I know it's a bit fast, but I hope you got the idea. It's a max flow, very nice max flow problem. And actually, there is another follow-up paper by Grigoriadis from Ioannina, who was at Princeton with Tarjan and I think Goldberg. I'm not sure about the third author, who actually proved that you can do parametric maximum flows and you can remove the logarithmic part. Okay. Okay, Goldberg's algorithm is very expensive because for each min cut, we need n times m runtime, n number of nodes, and number of edges. And basically, there is a simple greedy algorithm that gives a 1/2 approximation to the densest subgraph problem. So even if we have an exact method, we may do a greedy method simply because it's way faster. So you have a graph and you can compute the degree sequence here. So basically, you will keep removing the node that has the smallest degree. So originally, we have 2 nodes of degree 1, so we can remove either. Let's say I remove this one. Then I remove this one. Now we have nodes of degree 2. This has degree 3. So this and this one are the lowest degree. I can remove any of them, and I continue. And I create a sequence of graphs, right? So I started from the, what happened? Sorry. I started from the full graph, and then I keep removing a node at a time. So I create a sequence of subgraphs, and among this sequence, I output the one that achieved the highest density. And the claim is that this density is always at least half of the optimal density. So this is an approximation algorithm. It's another type of techniques and tools we use. And this is where my outline was, I want this talk to be a bit more theoretical because, especially I knew many of you are PhDs, is that for many papers, you need to, when you have a heuristic, which makes a lot of sense, you need to understand the limitations of this heuristic. And you need to be able to prove approximation guarantees or use randomization and so on. So this is algorithm. I won't prove it for you, but the proof is very easy. I strongly urge anybody who is seriously interested to try to prove this. Okay? Now, Tsarikar came up with another technique to solve this problem, which is called linear programming. He wrote down an ingenious program. It's a very smart linear program where every edge is attached to a variable, y. Y is upper bounded by xu, xv, where these are variables related to the nodes. We normalize the sum of xv's to be at most 1, and everything is non-negative. Linear programs can be solved in polynomial time. Well, there is some intuition behind this program. So basically, the nodes, the values xu, xv, try to encode which nodes will be in your output set, S. So if you have, let's say, something above 0, maybe you should include it. This is a key challenge when you design approximation algorithms using linear programming. Tsarikar proved that actually the optimum of this LP, linear program, is equal to the degree density, the optimal degree density. So if you solve this, the value of this LP, and I'm not doing the proof, but it's equal to the degree density. And he also showed how by solving this program and getting those values, x and basically x matter here, and y, but you get y and x, but you use x, you can use the x values to get the optimal solution. Now, the linear program is not such a practical thing. However, it serves a lot. And actually, I used it in my research to come up with an algorithm that combines the best of 2 worlds, the greedy and the max flow. So basically, with greedy algorithm, get the optimal result. But instead of running greedy once, you need to run it multiple times. And how do you do that? So when you have the primal LP, you also have the dual. You can associate to inequalities dual variables, and you can write the dual one. So there is the duality relation that says that the optimal value here is equal to the optimal value here. This is a result that gave Kantorovich, if I recall correctly, the Nobel Prize in economics. Okay, so the dual is always lower bounded by the primal, and if you see the dual, it says minimize variable d subject to f. You have some variables related to the edges. So every edge has some load, and you want to split the load of an edge to u and v. The load of each edge is lower bounded by 1, and your goal here is to minimize d, where the load that any node v takes from its incoming edges is upper bounded by d. So think of d like we have this graph. Let me show you an example. Let me show you an example here. So we have this graph, right? I think the primal, you'll understand. The primal, it's, I want to find this subset of nodes, which has this optimal density. The dual says every edge has a load of 1. And this edge must decide how to split the load. Will I put 0.5 here and 0.5 here? Maybe. You can make an assignment. Once you do an assignment, you can count for every node the total load that it gets from the edges that it's incident to. So if I split this 0.5, 0.5, 0.5, the load of A is going to be 1.5. Is this clear? So the goal is to split the loads, think of it as a game, such that you minimize the maximum load that any node takes. And the claim is this is equal to the optimal degree density. So for example here, I'm pressing the wrong button. If I split the load of this edge, EB, to go all to E, so the load of this one will go 1 to E, and B will get 0 from this edge, D will get 0 from this edge, F will get 1, and the rest of the edges split the load equally, 0.5, 0.5, then the maximum load is 1.5, which is exactly the optimal degree density. Why? Because the densest subgraph is this clique here, which has 6 edges divided by 4, it's 3 halves. Isn't it beautiful? Like how it's a very elegant result, right? So thinking of the densest subgraph problem as a load balancing game, you can come up with better algorithms. So what we did with a set of colleagues from Georgia Tech, we came up with an algorithm called Greedy++. And it's a bit technical, but I just want to give you the idea, right? The key intuition. So we will do greedy, but instead of running it once, I will run it multiple times. And I will think of a variable which is going to be the load of the node assigned in the previous iteration. So I will update the vertex degree according to the degree, but also the load from the previous iteration. And I will run greedy multiple times. So every time I will be removing the node that has the smallest, let's call it meta degree, okay? Because not just the degree. And this algorithm, you can actually see it here, it's very, again, easy to implement. And it initiated a whole line of research that Chandra Chekuri from Urbana and others followed to analyze this algorithm much better. You initially set the loads to be 0, and then you perform greedy t times. You find the node, in every iteration, you find the node with a minimum load from the previous iteration plus degree. You update the load with a load at its removal, and you do the same thing like greedy. You output the one that gives the highest density. And let me show you quickly what happened in some real data sets. So we tried it in many real world data sets. This is a whole table that includes social networks, technological networks, Twitter networks, trust networks, and so on and so forth. And some of the biggest ones had 140 million edges.
Yeah.
So
what is the importance of parallelizing these algorithms? Because it was, from your pseudocode, it seems to me it was like sequential, right?
Yeah, it's very sequential. Yeah,
but I mean, if you have such massive
there is a way
data
you can parallel. You can actually reduce the number of iterations by doing some smarter batching and bucketization of degree sequences. So I have a paper with Monica Henziger, Sayan Bhattacharya, and Danupo Nanokai from Max Planck that actually is trying to do something
on this problem.
Yeah. This came later, but the idea is you do some kind of approximate decomposition. So instead of doing n rounds of peeling, you can actually do much more, like logarithmic, and get something with, instead of 2 approximations, 2 plus epsilon approximation. So yeah, it's very important in practice. But what I want to show here is that we had max flow, which is very slow, very expensive, gives exact. You have greedy, which is very fast, but gives 2 approximation. Greedy plus in practice gave exact without solving max flow. And this initiated a lot of interest from the theory community. So basically, the number of iterations to get 99% of the optimum for most of the graphs, like more than 25 of the graphs, was like a couple of iterations. So running greedy for a couple of iterations gets you to the optimum. It was very nice. I had been thinking about this problem for quite some time, because you have these 2 worlds, it's like, how can you combine them? And why did I put the LP? Because all the intuition comes from the load balancing game. So you can see again how deep theory gets combined with very strong practice in industry systems. Okay, this, if I give it to you, anybody can go implement it. But coming up with this, you need to have some math intuition how to design those algorithms. So yeah, the scalability and the speed up were really very nice. So in general, the number of edges, you can see for large graphs, you can get speed ups which are more than 100 times. So it's, and as I said, it has been analyzed in depth. And actually, Tsekuri, what did he do? He actually said that you need to set the number of iterations of greedy in this way. I can tell you the parameters to get something which is epsilon far away from optimum. Depends 1 over epsilon square, and then you have some more parameters, max degree and log n. But basically, what Tsekuri did, he set the number of iterations to get optimality results. And you can actually see the speed ups 67.9, the largest was 290 times, and so on. So, any questions so far? Now, let me ask you, let me give another motivating question. So this finds a dense subgraph problem, but in some cases, you want to find large near clicks. For example, if you have a who calls whom network for security reasons, you may want to find a set of 30 people who all talk to each other, because they send a flagged anomaly in the system. Who talks with 29 other people and they all talk to each other. So finding these large near clicks is being used also in finding thematically coherent entities from Twitter. So you can have tweets, you can create graphs from those tweets. Joanna was talking yesterday about how you can get data and create graphs. And then once you have these graphs, you can try to do some algorithmic analysis. Well, if the edges have the semantics of co-occurrence, so you hear Bin Laden, Obama, these 2 entities during that period of time were co-appearing very often. So you create a weighted graph where basically entities that co-occur frequently create dense sets. So finding those dense sets allow to find stories that were not hashtagged, for example. Okay, so you do some kind of unsupervised discovery. And as I mentioned earlier, in Google, this is from a Google paper, you may want to find co-watch. So if you create a graph where the nodes correspond to videos and the edges, whether 2 videos were co-watched, finding large near clicks finds you topic clusters. So it's a recurring theme. How do we find them? Well, it's an NP-hard problem. Dense subgraph is polynomial time, max click is NP-hard, or even near click. By near click, I mean that some edges may be missing, okay? So, as I said, maximizing this objective doesn't make sense because it's maximized by a single edge. And if you try to set certain cardinality constraints to say, I want to find a set S of nodes where the set has at least k nodes, or maybe exactly k nodes, and maximizes the edge ratio, is NP-hard. Not just NP-hard, it's very hard to approximate, provably. So basically, what does it mean hard to approximate? No matter which heuristic you will come up with, it will fail in many instances, or in some instances. So this is what we call inapproximability. So max click is inapproximable. Even if you have a click of size order n, you cannot guarantee yet that your approximation algorithm will output something greater than n to the 1 minus epsilon for any epsilon. So basically something extremely small. So these problems are very hard to approximate. And let me give you an example why the DSP fails to find large near clicks. So this is a football network with 115 vertices and 600 edges. If you find the DSP, the densest subgraph problem, the average, the degree density is 5.3. But if you look, the edge ratio is 0.094. Why? Because it's not designed to find clicks or near clicks. However, in this network, there exists 18 teams with density almost 0.5. However, we cannot find it because it's a smaller set and its degree density is 4.1. So basically, it's not a mistake that doesn't find it. It's not designed to find these sets. So how can we find them? The question is, there exist many heuristics, and you can try one. The question that I asked was, is there a principled way? By principled, I mean well-designed way that provides a user not with a set of heuristics, but a principled way to change parameters in this objective to find those large near clicks? And the answer is yes. And this goes back to the question about the triangle motivation. Instead of looking just the average degree, we will look the average triangle density and or the average k-click density. So basically, I define this generalized k-click density to be the number of induced k-clicks divided by the cardinality of the set. So when k is equal to 2, a 2-click is an edge. So this thing, rho 2, is basically what I've been saying as rho so far. But when k is equal to 3, a 3-click is a triangle. So this is the average number of triangles in reality. So the problem is the k-click DSP, which is maximize the k-click density. We know how to do it for k is equal to 2. Okay? Can we do it for k equals 3? The answer is yes. In theory, these two differ a lot. So this is the triangle densest subgraph problem. For example, if you have a graph which is a union of a bipartite click and a single triangle, well, a bipartite graph has 0 triangles. So the densest subgraph problem will output this bipartite click, whereas the triangle densest subgraph problem will output this single triangle. The question is what happens on real data and whether we can do it efficiently. Now, without going too much into details, we can solve the k-click DSP for any constant k in polynomial time. And it relies on enumerating the set of k-clicks and then solving maximum flow. So it generalizes what I described earlier. I want to show you the effect that this objective has in practice, okay? So this graph is an opinions social network with roughly 400,000 edges, okay? So on the x-axis on this plot is k. So we'll talk about the k-click DSP. This is the k that I'm talking about. So k can be 2, 3, 4, and 5. On the y-axis, it's the size of the output, how many nodes it contains. So for example, when I solve the densest subgraph problem, I find that the optimal set has roughly 1,000 nodes. And for each one of those solutions, I scale the dot proportionally to the edge ratio. So this dot, this set of nodes, basically has edge ratio 0.12. What do you observe? As you increase k, the output size drops and the edge ratio goes up. It goes up to 0.5. What does this show you? That you can find the large near clicks in a graph by solving the k-click, assuming you can extrapolate from opinions, and you can for many real-world networks, by solving the k-click DSP for increasing values of k. Of course, this comes at a cost because it's slower. So this one you can solve in 2.37 seconds. This, if you do exactly, it takes almost 38,000 seconds to run the max flow. This is the effect of max flow. However, we have already discovered something, that there is a principled way to do that. And this replicates over many data sets. This is an astrophysics collaboration network and an email network. So you can actually see the densest subgraph problem gives edge ratio 0.09. The 5-click gives you 0.96, almost a click of 62 nodes. That would be otherwise very hard to find. Same thing here for the email network. As I said, this comes at a cost. So the next question we had to answer was how to make this faster. And this is where all these concepts of sparsification that I was discussing before come into play as well. Let me show you something more. We solved the triangle densest subgraph problem and the densest subgraph problem, so K2 and 3, for a time evolving data sets. And we noticed that basically you can actually see the number of edges and the number of triangles. But if you look the optimal solutions for every year, the triangle density explodes. What does this indicate to you as, let's say, practitioners? So you have this time evolving graph. You see that it doesn't have many triangles in general, more edges rather than triangles. But somehow, if you try to find the densest subgraph versus a triangle densest subgraph, the triangle density explodes. This is like an anomaly. Why is this? Like you ask, the triangles evolve slower than the edges, yet the optimal triangle density goes much faster. This happens because there is a pharmaceutical company that every time it was citing a patent, issuing a patent, it was citing all of its previous patents. So it was creating some large near click that was exploding the triangle counts within this set. So you can use this to find citation rings, or it's very interesting to try it. I didn't show the results, but is that clear?
But can one company affect the whole?
It was a subgraph, yeah. It's like a very dominant company. Yeah. So when I went and looked what was going on in the set, it was all Allergan.
But maybe it's also power law. You have more.
Yeah, you may have more. It's just a demo to show that you can find anomalies using these tools as well. So now, how do we speed things up? Well, just a concept definition. What is a hypergraph? Well, a hypergraph is a generalization of a graph where basically an edge may connect more than two nodes. We were talking earlier with one of you about hypergraphs. So if I think of every k-click as a hyperedge that connects the k nodes that participate in that, I can think of the k-click network as a hypergraph. And this is a very general theory. If you have a hypergraph and you take 6 n log n over epsilon square hyperedges uniformly at random, then if you solve the densest subgraph problem on this subset of edges, then you get 1 plus epsilon approximation. Now, notice that the number of hyperedges can be n to the power of k. You can have n to the power of k k-clicks. So a hypergraph is a general object, but I think of the hypergraph in this context as a hyperedge that connects all the nodes that form a k-click. How many k-clicks can I have? N choose k, right? So asymptotically, the number of hyperedges in the hypergraph can be extremely high as k grows, right? However, keeping only n log n over epsilon square of them suffices to get a 1 plus epsilon approximation. And this is how you see how all this machinery can lead to very efficient algorithms. It's a technically difficult theorem to prove in the sense that chain of bounds gives polynomial failure probability and you have exponential number of sets, but with a trick you can actually make this work. So what do we see? Let me show you something. Depending on, first of all, if you sparsify with P, you get space reduction 1 over P. And if you assume you do maximum flow, the speed up is 1 over P squared. Depending, on, of course, on the black box max flow algorithm that you use. But the key thing here is to show that for k is equal to 2, we get only 3-fold speed up. Why? Because when k is equal to 2, your input is actually the graph, right? K is equal to 2 are edges. 2 clicks are edges. So because real world graphs are sparse to begin with, you don't get a lot of speed up. And the accuracy is 95% across all experiments we did. But as you increase k, for the graphs that we were able to run, the exact versus our approximate version, we get up to 24,000 times speed up. Why? Because there are so many 5 clicks. And you can throw away most of them, keep just a linear number with respect to the number of nodes, and you can get a very high accuracy. So this is why we came up with this theorem, the densest subgraph sparsifier, because we were interested in the k click for k larger than 2. Because for k2, okay, you get 3-fold speed up, it's very important, but see what's going on here. And this is, as I said, for many graphs, you cannot solve the k click unless you sparsify. Sorry, again, same mistake. So this is a more, let's say, zoom in version of the result. So here you can see k, here you can see the edge density. the more close you are to a near click. So you can see as you increase k and you solve the problem, you start getting higher edge ratios, which agrees with what I said, that you start finding large near clicks. The output size drops, yet it remains non-trivial. It remains several hundreds of nodes. So from over 1,000 nodes, you go down to a few hundred for K5 with edge density from 0.1 to 0.5. And because it's randomized algorithm, so for every K, I run it 5 times, you can actually see those points exactly. And you can see that the accuracy, because in this case, I can solve the exact version. It's not a very large network. You can actually see that the accuracy is lower bounded by 95% in all cases, and sometimes gets higher. And the speed up goes from almost 4-fold or 5-fold for the densest subgraph problem to more than 2,000-fold for the K5 problem. Okay, so just to summarize, I've shown you several tools. We solved the densest subgraph problem. I showed you how to solve it exactly using maximum flows. I showed you, just a recap, a greedy version, which is very nice and provides a 1/2 approximation. I showed you the greedy plus, which is greedy many times and achieves near optimal results without max flows. And we also saw a generalization of the densest subgraph problem called the K-click DSP, which allows practitioners to solve a very challenging problem in practice. Any questions so far? These are a lot of papers and they're very technical. So I just want to reveal some of the intuition and some of the tools. And for those interested, you can go and you can read more details. And feel free to email me if you have any questions. I'm open to students. So, if you have any questions, I'll be happy to reply. Okay, community detection. So no questions. So let's move to community detection. So I talked about how do you find one subset of nodes, a dense subset of nodes or a click. In some cases, we want to partition the graph into various sets. Let me show you for a moment. So if we go to, by the way, this paper that I'm going to show now, Dimitris told me to tell you, I co-authored it with Jakub Paczocki, this theory paper, and Jakub now is the director of OpenAI. So he was an instrumental person in developing ChatGPT. And he was doing pure theory. He went to deep learning from pure theory. Jakub was doing Laplacian solvers. So basically, what I was talking about Laplacians, if you have a linear system Lx equals B, how do you solve this system very fast? This was his PhD, like a big chunk of his PhD. So what I want to show, I want to show you basically. So let's see InfoMap. Okay, so in general, graph database companies and general knowledge graph companies, they offer standard community detection algorithms. They're very widely used, and actually we record the usage by customers. Community detection is a very, very frequently executed task. So let's see InfoMap. So here you can actually see they have a notebook, but what I want to show you is basically label propagation, Louvain, InfoMap. They're all community detection algorithms, okay? And Jupyter. So I won't run this now, but basically there are notebooks where basically you can create a person and a friendship. So this models the nodes and these models, let's say, the friendships. The model creates a database. So you create a database and 2 entities. Then let's say you have some data. You have Mary Bob with weight 1 and so on. So you add your edges from your dictionary or your snowflake table if you have a big data set to your database. And the way you do it is you add each one of those names to the person entity and each edge to the friendship entity. Then once you have those, you can, like your database, which is the model, you can create the graph, you can set it to be undirected, you can set it to be unweighted if you want. There's another flag, let's say it's weighted. And yeah, this is just adding the edges from the friendship relation to the graph. And we basically extend the node entity from the graph to be basically the persons, okay? And the way you run the algorithm is very, very convenient. So you say with model.rule, P is a person. So basically, P is an entity of a person. You compute the community that P participates in. And you set this to be a property of the node, let's say the community ID. So if you run this, you can actually see, okay, here they show the edges. And so basically you can see Anna is participating in community 1, marking community 1. So basically we're printing here the set of edges and the community IDs of the nodes. But you can also just print the nodes and their community ID. So yeah, something like this. So as I said, these are like industry style algorithms. Louvain is very popular and very well performing. And today I'm going to show you an idea that basically extends random walks using the help of triangles. So I spent all this time about triangles. We said there's a lot of motivation, but let me show you with this simple idea of what you can do. This is joint work with Michael Mitzenmacher from Harvard and Jakub Paczocki from OpenAI. So basically, instead of doing the random walk, where basically at node U, I choose one of the neighbors uniformly at random, I choose one of the triangles that U participates uniformly at random. And then among those triangles, I choose one of the endpoints of that triangle uniformly at random. So U participates in 2 triangles, UVW and UZW. So let's say I choose this one, and now I have V and W, and I choose, let's say, W with probability 1/2. So what you can see here is you're biasing the random walk somehow, right? This node that you had before probability 1/4 to go in the standard random walk now has 0 probability, and node W has higher probability than any of the other 2. Why? Because it participates in 2 triangles together with node U. So let's see what we can get in theory from that. How much time do I have?
Well, around 25 minutes.
Okay. So yeah. So given a set S, I can define different types of triangles. So the one is the one that is induced. This is how we called it, where all 3 nodes are inside the set. But then you can also have a triangle with 2 nodes inside and 1 outside versus 1 inside and 2 outside. So when I define a random walk like this, the first thing I want to do is understand the conductance, the new type of conductance I'm defining. So the conductance that I defined earlier, as I said, is an escape probability. So I'm inside a set, I wish I could write to show you the contrast, but in the standard random walk, where I have a set S, and I do the random walk, the conductance is the probability of 1 step escape from this set, assuming I start the random walk from a node inside the set with probability proportional to the degree. What is the conductance here? Like if I define this new random walk, what is the conductance here? Second question, I showed you Chigger's inequality and spectral clustering. Can I extend the idea of doing these cut algorithms that find some kind of clustering of the graph, or instead of thinking about cutting the edges, I'm cutting triangles? Why? Because if you are a community, most of the triangles will be even more pronouncedly contained inside rather than outside. So maybe this is helpful. We'll have to check. But just think about a simple theoretical idea opens up many questions, okay? Another very interesting theoretical question. I said expander graph. But an expander graph is a graph that has no set with low conductance. Is there a triangle expander graph that is not an expander graph? And is there an expander? So you see how a simple idea opens up many research questions. I have to say also that at the same time, just to, and I should also add to the slides, Yura Leskoves, David Gleich, and Austin Benson from Stanford, we published simultaneously in separate venues similar ideas. However, our version of the paper takes a much more well-founded notion of the conductance based on random walks. Whereas they said, okay, let's try to minimize a cut function where in the numerator we have a function of the triangle's cut divided by the volume of the triangles. But our object is very similar, but has interpretation of the random walk. Okay, and yeah, let me show you the paper immediately. So this is one sec. So Benson, Leskovets. So this was published in Science. Okay, this simple idea of with numerous applications, and the title of the paper is Higher Order Organization of Complex Networks. Okay, so yeah. So we have these types. This is a useful definition for the next slide. So if I think of a new notion of conductance, which I subscript using the triangle size of a click, 3, phi 3 of S, the probability of leaving S in one step of the random walk condition on being at a vertex chosen from S proportional to the number of triangles. So I'm extending the definition of conductance to the triangle conductance. Then I can actually do a calculation to compute this probability, and turns out to be the number of type 2 triangles plus the number of type 1 triangles divided by the volume of S, subscripted by 3, which means I sum over all nodes in S, the number of triangles at each node participates in. All this stuff required triangle counts. You see how triangles, we started from the very simple problem of counting the total number of triangles, and we have gone to science level papers from triangle queries, okay? They're very useful in social network analysis, in finding cohesiveness of sets, clusters of sets, anomalies. For example, let me do another digression. If you have a social network and you do the following thing, compute the degree sequence, and for every node, compute the number of triangles of that node. So basically, every node has a degree and the triangle count. And you do a scatter plot of this. If you see a high degree node with low number of triangles, what does this indicate? Probably some advertiser, right? There know many random people who don't know each other. So basically, you can actually get a lot of information about this sort of the graph structure just from those simple counts. And people have used it in anomaly detection. I had in one of my papers, I had actually tried to ask the following question: if in the future, let's say I have a graph, okay? If in the future this graph evolves and the number of edges doubles, what will happen to the number of triangles? Will it triple? Will it, like, how will it grow as a function of the number of nodes? And I answered this question empirically by detecting laws using triangle counting algorithms, which actually gave you a pretty good sense of how counts would evolve. These were called triangle power laws. And if the number of edges double, roughly the number of triangles triples in many social networks, which is an empirical thing. There's no proof for that. Okay, so this is done by fitting some kind of power law and then extrapolating. So now we go to this usage of triangles, and I will call a graph a triangle expander if there is no set of nodes S. We set it to be at most half of the nodes because of symmetry. If I have a set S, then I have the complement, so I don't need to have this redundancy. So for any set of nodes S, if the triangle expansion is constant, then it's called an expander. So basically, this probability is constant. It doesn't drop as a function of the number of nodes in the graph. Because you can have a graph where the conductance is low, right? If you have a path graph, try to do this as an exercise. If you have a path graph, or maybe an even more pronounced, suppose you have a click on n nodes, another click on n nodes, connected by an edge. What is the conductance of this graph? Well, we said the conductance is the minimum over all sets, but because the structure is very clear, if I have a click here, another click here, and they're just connected by an edge, clearly the best way to cut it is by removing this edge, right? So what is the conductance? It's the size of the edge cut, size, which is 1 in the numerator, divided by the volume of the set or of its complement. In both cases, it's roughly n squared. So the conductance of this barbell-like graph is 1 over n squared, which is very, very low. So the probability goes to 0 of escaping from your set as n grows. It makes sense. As you grow those cliques in the barbell graph, the probability you will stay inside goes to 1 rather than leaving your set. So this is why you have this asymptotic here, this asymptotic notation. Now, if we take G and P and we set P to be log n divided by n to the 1/3, then we can prove with high probability that G is a triangle expander. And we have this conjecture that even if you set n to be 2/3, so you make the graph even sparser, this thing still holds. And we also proved in the paper with Jakub and Michael that basically you can have graphs that are edge expanders, but not triangle expanders, and vice versa. So the two concepts, this is like, as a theoretician, you need to prove that this new concept is different from an existing one. This is why this is useful here. And now we have an elegant variation of the spectral clustering algorithm, which probably gives you approximations for the triangle conductance. So basically, if I want to cut a graph, and instead of caring about edge cuts, I want to care about triangle cuts, the algorithm goes like this. For every edge, count how many triangles it is contained. So again, we have triangle counting. You reweigh your graph, and then you apply your favorite clustering on this reweighted graph. And by doing spectral clustering on the reweighted graph, you get a Cheeger type inequality for the new notion of cut. Okay? And all of this is useful because for many empirical networks, doing triangle cuts gives better quality communities compared to just doing the conductance. One interesting observation is that when you take a connected graph, let's say one connected component, social network, let's say this is YouTube, Amazon, DPLP, this is co-purchasing graph, this is co-authorship graph, and you have also YouTube graphs. So basically, if you take this unweighted connected component and you count the number of triangles and you reweigh the edges, without even doing spectral clustering, you disconnect the graph in multiple components immediately. So you immediately get some kind of partition of the graph. Why? Because many edges, like think about the barbell case, right? Think about the barbell case. In how many triangles does the edge that connects and participates in? Zero, right? So think, you have a click and another click, disconnected, and then I connect them with a single edge. This edge, how many triangles is it contained inside? Zero, right? These two nodes, the endpoints, one has neighbors in one click and the other on the other click, and the two sets are disjoint. So just by reweighting this edge, the graph gets disconnected into the two communities without trying to do any cut. So basically what you can see here are the triangle component sizes. It's a histogram. So you can see there is a large, let's call it giant component. And then you have a bunch of smaller connected components that follow this cute distribution, which follows some intuition. You have some kind of very well connected set of nodes. This has been established by Yuri Leskovets many years ago that claimed that you have some kind of core periphery model where you have a big core which is very well connected, and then you have communities attached to this core in with fewer edges. Okay, so this would explain this remark here. So here is an algorithm that Jakub and I worked on and actually provide very simple heuristic and provided state-of-the-art community detection results. And it has been used by Google Research. I can actually open and show you the graph mining group from Google Research led by Vahad Mirokni. They have designed also other algorithms based on correlation clustering and other techniques that are competitive to this very simple heuristic. Let me tell you what the heuristic is about. Count number of triangles for every edge. Reweigh every edge by the number of triangles, but we normalize by the decrease, similarly to the normalized Laplacian. the sum of degrees works pretty well. You can try different things. It's not like this is the only way it can work, but we normalize by the sum of the degrees. This resembles a little bit the Jacquard coefficient, because if you think about the two nodes and you think about their neighbors as sets, the intersection of those two sets, assuming UV are connected, is a count of triangles. So intersection of one set and the other gives you the number of triangles, and the denominator is the union of the two sets, which basically is the sum of the degrees minus the number of triangles, but we don't have the minus there. So it's very close to being a Jacquard similarity of the neighborhoods of the nodes. So you reweigh every edge by the number of triangles divided by the sum of the degrees, and then I use the observation from the previous slide that by reweighting, we disconnect the graph into numerous components. So basically, we do a connected component calculation on this sparsified, hopefully, graph or disconnected graph. This is a heuristic. And it also, we made connections to hierarchical clustering, where basically this is less than theta if the Euclidean square distance of the adjacency rows is greater than theta prime, where theta prime is this function of theta and the degrees. But let me show you this heuristic, which is called tectonic, how it compared to some state-of-the-art papers. So this is spectral clustering, threshold 0. Sorry, these are disconnecting based on the counts. This is tectonic, so please look at this edge, this row of this table. This is SEs for spectral clustering. It didn't complete on these edges. Neither did the spectral clustering. It was very slow. When you want to do this eigenvalue, eigenvector computation on very large graphs, it can be slow. Here is Louvain. Here is Markov clustering, and here is InfoMap. These are some of the best performing methods. So we used it on graphs, these three graphs where we have the ground truth communities. So basically, we can evaluate if how well we did, right? If we classify nodes properly or not. So we have precision and recall. You can see MCL here has high precision and pretty good recall in 736 seconds. Here 55, 81%, 39, almost 46%, so on and so forth. Louvain and InfoMap, they're very close, and you can also see the runtimes. Take a look at tectonic. 94.9, 91.3 in 4 seconds. 48.3, 79.1 in 1.65 seconds. So you can see the numbers. Like, it's already comparable to some sophisticated methods. And what do? Triangle counting and connected components. And you already find structure that you need to run some very sophisticated. The InfoMap is essentially a compression algorithm. You do random walks, and you're trying to do a compression of those random walks. If you find the communities, you can compress them better. This is a key idea. Louvain is looking into the modularity objective, and it's basically a smart greedy algorithm on how to optimize modularity, which captures, it's similar to the conductance, but it's a different measure, if you want to think about it. So I think this is an important finding. And one thing I'd like to point out is that, take a look, as the ground truth community size increases, the precision goes high, the recall goes down. What does this tell you if you see this plot? As a data scientist. So each dot corresponds to basically a ground truth community, right? And we see the precision in the sense how many nodes from this community did we say that they're indeed from this community, right? And the recall. So compared to the full size, how many did we find? So what happens is that basically the precision increases. So if you have a community with, let's say, 300 nodes, we output something smaller, maybe 80 nodes. They all come from this community. So we're precise, but at the same time, the recall drops. So we cannot find the whole community of 300 nodes. So this is an interesting practical problem. How can you improve this? In general, in non-supervised learning problems, being from graph detection to time series, where you may want to find structural breakpoints. So, for example, I give you stock prices, okay? And Trump announced tariffs on April 2nd, the Liberation Day. So this was a breakpoint for markets, okay? You may want to find it in an unsupervised way. This was a breakpoint we know, and maybe we want to say that an unsupervised algorithm should find it. But in general, when you have time series, you may want to find those breakpoints. And how do you evaluate that? How do you evaluate communities? In general, unsupervised learning is a pretty challenging domain. So I showed you some methods for, so I'm almost at 6. I don't have much time for the node embedding stuff, but what I want to say is that if you go beyond this stuff, there exist problems related to fairness. How can you find clusters that have fairness guarantees? You may want to deal with opinion dynamics and like now with LLMs, you can parse tweets, you can parse text, you can get a good sense of the sentiment on the top of a network. So you may want to find, let's say, sets of items that also have some extra constraints. I was discussing about with one of your colleagues about a version where there's a problem, well studied, but then there are extra constraints. So these tools, there are many problems that go beyond them, and they have a lot of applications in graph mining. I touched a bit the node embeddings, their beginning using the Laplacian embeddings. Didn't have time to go a little bit deeper into the more modern embeddings, but I want to outline that the foundations will serve you to go there. So if you understand, so the theoretical results I've recently proved in ICML and Eurips, this is where you start from spectral graph theory, but you end up giving, let's say, nonlinearities, and you need to understand nonlinearities. What was the tool I want to show you today? The sign rank of a matrix, which is something different from the rank. I didn't have time to get there. But I hope today this session has motivated you to look deeper into this, has shown a set of techniques and how we can start from a very simple problem and end up with a rich set of applications that go from theory to basically industry. And I won't start a new session because it's almost 6, but we have like 8 minutes, and I would love to hear more questions or have a discussion with you. So thank you so much.
Thank you. Of course, we will, you can also speak to the speaker in case you have ideas or questions or collaborations. Many people say that summer schools are great opportunities to create collaboration links. Have anything? So just a question on how to go about, development also from a more practical perspective. So you have you showed the Louvain algorithm, I think, and I kind of thought I saw it also in the platform you already have. So the relational AI.
Yes.
So then, I mean, what is the general, approach to this? You revisit the problem with another perspective, or you try to improve continuously? I mean, is it open-ended?
Yeah,
You're not satisfied at some point, and then think we work on other operators, maybe?
This is a great question, because in a company, you have program managers, and they play a big role in the way they interact with clients and the feedback. For example, Louvain. It turns out it's a priority to make it available because people use it. Okay. For example, there exist other algorithms, like I mentioned MCL. I would like to implement it, but it's not a current priority. So it's much more customer driven, at least in a startup environment, in my view and my experience so far. At the same time, there must be all the foundational stuff that we're discussing earlier about clicks, triangles, etc., etc. And they need to be optimized so you can analyze joins efficiently on basically conjunctive queries in a very efficient way. I like this. I try to bring together from the triangle query, Loomis-Whitney inequality, from geometry to joins in databases to graph algorithms to randomization. So I really like this concept. I think it's a good choice for students who are interested in theory in a summer school to get exposed through a simple problem to many challenging techniques. But to go back to your question, I think in a company, much of the product delivery depends on the customers and how they prioritize. At the same time, on the backlog, you have issues that you try to work when there's no pressing issue. So, for example, you say, I want to have this algorithm eventually. It's not a pressing demand right now, so it's in the backlog on Jira, but we have this thing that we need to deliver either as experimental or preview. What you see on the webpage are basically not experimental features. It's like a product level. And you can actually see how an algorithm that I can implement in a few days to get to the product version takes months of testing, deployment, CI/CD, continuous integration, continuous development. It's way more complicated when you.
And some you said that they are heuristic based, so that these presumably will not make it there.
No, they won't make
They
it.
will,
Yeah,
even
if they're
it's
established, if people know that it works, if Louvain works well. So basically, if you see Louvain and Informat on the webpage, there are some parameters. Now, the question is how you choose your parameters, right? We can run for a given setting. One could say that you want to choose, what we can do is choose the best possible defaults in some way.
But no correctness results are required, like in the general.
It's correct, because what you ask, you got it. Now it's up to you to see if your output was correct. As I said, for unsupervised learning problems like community, you can actually do the following. You get some partition, you can actually go and you can look the conductance of the partition or the modularity. So it's very simple to have those measures. You can run them on the output and see if the measures that you get agree with what you got from your Infomap or Louvain.
So one question in the back.
Yep.
Yep.
Yeah, thanks for the talk first. And like from a practical or implementation standpoint, have you dealt with like parallelizing these algorithms? Like, is it generally hard to parallelize them, or even like?
You mean in the company or in general?
I mean, the papers are probably like mostly on the algorithmic perspective, but maybe in the company when like actually implementing these algorithms.
There exist multi-threaded attempts that have been done, and there is a parallelization team, but this abstracted from. So you have different teams. One is infrastructure, one is query optimizer, the other is the parallelization team. So you try to make it modular, and of course there is communication when, for example, you see in the logs that something broke down in one task, and you have to communicate with another team to fix whatever. But in general, parallelization is important, of course, and I think there's a lot of interest in parallelizing things, both from theory and practical perspective. Many things work on the cloud, and this has its constraints on how you do things. And your computational model and many aspects. For example, when you have the cloud, you want also to minimize the communication overhead to get the results. And this can be significant, right? You need to spend some effort in optimizing. So in practice, to deliver a product, there are many angles that you need to be careful about. But from a theory perspective, you can easily find pointers on Scholar. And if you want, you can shoot an email and I can tell you. But parallel triangle counting algorithms, parallel density subgraph. So it's a lot of yeah. Actually, had the paper with one of my students where we looked.
Let me show you, since you asked. So if you go to my webpage and you go right here, publications, and you go to parallel motif-based community detection. So this was something that we did in terms of parallelization of those things. So it's quite an important task. But this gets to be a bit more engineering. So I focus more on the theory side of things.
So I also wanted to highlight that we try to bring in different theoretical foundations for data processing systems. Graphs is definitely one. The next few days we will focus more on spatial also, spatial temporal. And it's clear that each of these data processing in AI stacks will put strengths on different aspects. And it's nice to see that also, as we know from traditional data management system, relational algebra has been foundation, let's say, for doing things. And now if you have graphs, you need some theory, graph theory basically, which is basically what you're doing, the theory on graph theory, is it foundation for this. And so at this point, I wanted to ask something because I also noticed there that the strength, when you were showing the relational AI, it had graphs just as one pillar at the end, and it had other things as well. Is this is this focus also spanning into other things?
Yeah. If you ask me
Beyond
relational
maybe-
AI, it goes beyond graphs. So
Which is what? Because I saw
I'm not sure if what you're referring to, I can check, but basically it's the more holistic data management. So instead of SQL, it goes to the data log side of things. So in that sense, it's a data management system. It has optimized joins, recursions, and this sort of machinery that is very common. But for example, I know clients that do tax-related tasks where you have many rule-based sort of things. You may want to raise a flag if you see this sort of thing. This type of.
So it's one-stop shop everywhere eventually.
Yeah. So it's way more good.
So if we don't have any other question, let us take the speaker again. We have the pass now recording, so you can collect your stuff and then move on to the bus station. It takes us directly to the restaurant. Okay, and from there the hotel will be about 15-20 minutes walk in the back. It's pretty safe. It's not too far, and we will be done. I guess by 9:30, 10 o'clock, the latest. So can you pick up? And